Welcome to the course, Machine Learning with Hands-on Experience in Python and R, under Part 2a, such as, Simple Linear and Multiple Linear Regression. This course is fun and exciting, but at the same time, we dive deep into machine learning. It is structured the following 10 parts to be the master machine learning on Python and R. This video we will discuss about the Part 2, Regression, Simple Linear Regression, Multiple Linear Regression into the following ways. First we will discuss about the simple linear regression and how to do it in practical way.
Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click, extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning. What we see here is 2 columns, very simple dataset: years of experience and salary. And basically it's telling us for a given company there's 30 observations, and they took 30 random people and said, all right, so how many years experience do you have? This is not just with the company, this is overall years of experience in the workforce. And what is the salary of that person? And then what they did is they wanted, or they've asked you, they've hired you as a data scientist to find out if there is any sort of correlation, or what is the correlation between salary and years of experience. So this is one of those cases when management obviously knows that there is a correlation, that it's they set the salaries, right? But maybe it's like it's a new company, maybe they only have 100 employees or something, and they've been kind of setting them randomly so far. They know that, you know, experience matters, and they've been taking it into account when when setting the salary for a certain employee. But there's always this range within which it fluctuates, and they've got like ballpark estimates that they are adhering to, but they don't have a certain strict rule. And what you're going to be doing in this section, well, first of all, you're going to investigate what is the correlation. Well, obviously it's probably going to be the more years of experience you have, the higher is your salary, and we kind of can see that trend already. But we will actually be creating a model, a simple linear regression model, which will tell us what is the best fitting line for this relationship. And if you want to look at it from a business value add perspective, what is the business value add of this project? Apart from us, of course, learning about simple linear regression, the business value add here is that if the company doesn't know they don't have a certain set of rules how to set salaries, you can then go back to them with this model and say, okay, actually, this is how so far you've been setting salaries, and if you want to continue, then this is the model you should be applying, plus or minus a certain deviation. But you'll be able to tell them for future employees, say here you can see there's only somebody with 10.5 years experience. So what do they do when somebody with 15 or 20 years of experience comes into the company? They can either randomly guess a number, or they can use your model to set them a salary that everybody else won't feel uncomfortable with. So something like that. So there is a business value add even in a small project like this. And let's get started to learn and practice simple linear regression. A simple linear regression is basically this formula where y equals b0 plus b1 times x, and you might recognize this formula from back in high school. It's just a formula of a trend line or a sloped line on a xy axis. And let's go through these variables and coefficients one by one. So this is the dependent variable. The dependent variable is something you're trying to explain. For instance, how does a person's salary change with the years of experience that he has? So in that case, y would be the dependent variable. Or what grade does a student get depending on how much time he's put into studying? In that case, y would be the dependent variable. So something that you're trying to understand how it depends on something else. X is your independent variable. In this case, in the simple linear regression, we only have one independent variable, so we don't even have to call it x1, we could just call it x. And this is the variable that you're assuming that it is causing the dependent variable to change, or as we will learn further, sometimes that independent variable might not be a direct causing factor, but it's still, there might be an implied association between the two, and in that case, you're trying to figure out this association. Then b1 is the coefficient for the independent variable, and it kind of says how the effect, or how a change in x1, a unit change in x1, and we'll be talking about this a lot, unit changes. A unit change in x1, how that affects a unit change in y. So it's kind of, think of it as the translator or the multiplier or something like that that connects the two, the connector between y and x1. So you can't just say, you can't always say x1 is directly proportional. There is, well, you can't just say y, the change in x is always equal to the change in y. There might be this coefficient of proportion, to which proportion that change is inflated or deflated. And b0 is the constant, so it's a constant term, and we'll talk about the constant just in a few seconds. So now let's look at the simple linear regression, because it's the easiest one to discuss. It's very pretty straightforward. You can visualize it quite well. So here we've got the y and x axis. Let's look at that specific example where we have experience and salary. So experience is going to be our horizontal axis, salary is our vertical axis. And we want to understand how people's salary depends on their experience. Well, what we do in regression is we don't just come up with a theory, we look at the evidence, we look at the live hard facts. So here are some observations we've had. So in a certain company, this is how salaries are distributed among people who have different levels of experience. And what a regression does is, so that's the formula for regression. In our case, it'll change to salary equals b0 plus b1 times experience. And what that essentially means is just putting a line through your chart that best fits this data. And we'll talk about best fitting in the next tutorial when we're talking about ordinary least squares. But for now, this is the chart, this is the line that best fits this data, and it even looks like it, right? So it's quite hard to draw a line that fits this data better. And the assumption here is it's impossible. This is the best line that approximates this data. What does that mean? Well, we'll talk about that in the next tutorial once again. For now, let's focus on the coefficients and the coefficient and the constant. So what does the constant mean here? Well, the constant actually means the point where the line crosses the vertical axis. And let's say it's $30,000. What does that mean? Well, it means that when experience is 0, so when, as you see on the horizontal axis, when experience is at 0, then in the formula on the right, you can see that the second part, B1 times experience, becomes 0. So salary equals B0. That means that salary will equal to $30,000 when a person has no experience. So as soon as somebody's fresh from university and joins this company, most likely they will have a salary about $30,000. There will be some confidence intervals there, but we won't go into that right now. Just we can say that according to this model, that person will be probably getting paid $30,000. Now, what is B1? B1 is the slope of the line, and so the steeper the line, the more you get, more money you get per extra year of experience. Let's look at this in this particular example. Let's say somebody went from I don't know, maybe 4 to 5 years experience, right? So then to understand how his salary will increase, you have to project this onto the line and then project that onto the salary axis. And you can see that here for 1 year experience, the person will get an extra $10,000 on top of his salary. So if the coefficient B1 is less, then the slope will be less, and that means the salary increase will be less per every year of experience. If the slope is greater, then that means the experience will yield a more increase in salary. And that's pretty much it. That's how a simple linear regression works. So the core goal here is that we're not just drawing a line theoretically that we came up with somehow. We're actually using observations that we have to find the best fitting line. And what a best fitting line is, we'll talk about that in the next tutorial. In the previous tutorial, we talked about the linear regression being a trend line that best fits your data. Today, we'll find out how to find that best fitting line, or in fact, how the simple linear regression finds that line for you. So here's our simple linear regression, the same chart, salary versus experience. We've got these red dots which represent the actual observations that we have in our data, and we've got the trend line which represents the best fitting line, or the simple linear regression model. So now let's draw some vertical lines from the actual observations to the model. And let's look at one of these specific examples to understand what we're talking about here. So here you can see that the red cross is where that person is sitting at in terms of salary. So let's say this person with 10 years of experience is earning $100,000. Well, the model line, so the black line at the bottom, it actually tells us where that person should be sitting according to the model in terms of salary. And according to the model, it should be a bit lower. It should be somewhere where that green cross is, which is about maybe, let's say, $80,000. So now the red cross is called YI, so Y with the subscript I, and that is the actual observation. The green cross is called YI hat, and that is the modeled observation, or the modeled value. So basically, with that level of experience, where would he be? Where does the model predict that he would be earning? And so the green line, therefore, is the difference between what he's actually earning and what he should be earning. So, or not should be, what he's modeled to be earning. So, therefore, the green line, it will be the same regardless of what dependent variable you have, whether it's salary, whether it's grade at school, whatever. So it's the difference between the observed and the modeled for that level of independent variable. Now, to get this best fitting line, what is done is you take the sum, you take each one of those green lines or those distances, you square them, and then you take the sum of those squares. Once you have the sum of the squares, you gotta find the minimum. So basically, what a simple linear regression does is it draws lots and lots and lots of these lines, these trend lines. Well, this is like a simplistic way of imagining it. The linear regression draws all these all possible trend lines through your data and counts the sum of those squares every single time, and it records it somewhere in a temporary, file or something like that, and then it finds the minimum one. So it looks for the minimum sum of squares. It finds a line which has the smallest sum of squares possible, and that line will be the best fitting line, and that is called the ordinary least squares method. So that's how the simple linear regression works, and I look forward to seeing you on the next tutorial.
Hello and welcome to this Python tutorial. I'm super excited because we are going to implement the very first model of machine learning. We're going to start with the most simple one. It's the simple linear regression model. So let's do it right now, and let's do it on Python. So we're going to first do it on Python and then we'll do it in R. And for both, it's going to be a step-by-step approach. So the first thing that we need to do is to set the right folder as working directory. So to do this, we need to go to File Explorer here. Then you have the Machine Learning AZ template folder, so let's go inside. Then we go to part 2 regression, and then simple linear regression. And here is the right folder. That's the folder we want to set as working directory. Make sure that you have the salary data CSV file. That's the CSV file we're going to use to build our simple linear regression model. So let's make sure we have it. And if that's the case, now we need to click on this little button here to set this folder as working directory. So now it's good. And now we're ready to start. So the first step of making a model is to pre-process the data, and of course we're going to use our data pre-processing template that we made in part 1 to complete this step very efficiently. So let's just copy all this. That's the data pre-processing template. Let's copy this and let's put it in our simple linear regression Python file, and let's paste it here. And now we need to change a few things. Well, first we need to change the name of our dataset. Here it's not data.csv but salary data.csv, so let's change it right now. Salary data.csv. And now let's see what we need to change. Okay, so first let's import the libraries to get the essential tools we will need to build our model. And here, as you can see in the IPython console, the libraries are well imported. And now let's select this line and execute to have a look at our dataset. So as you can see here, the dataset is well imported. And now to have a look at it, we need to go to Variable Explorer, and then appears here the dataset. So let's double click on it and let's explain the problem. So first of all, let's perhaps change the format because we have the scientific notation. Maybe we would prefer something like with no decimal and regular floats with no decimal. So to do this, we need to change this 3 here, which is the number of decimals, by 0, and this G by F. And then you'll see that if I click OK, I'll get my salaries in this format, which is, I think, better. So, okay, so this dataset contains 2 columns, the year's experience and the salary. So basically, these are informations of employees in a company. The first column, year's experience, gives the number of years of experience each employee has in the company and its respective salary in the salary column. And so we have 30 observations, that is 30 employees for which we have those informations, because as you can see, the index started at 0 here. And so what we'll do here is that we will train a simple linear regression model that will learn the correlations between the number of years of experience each employee has in the company and its salary. And by understanding those correlations between the number of years of experience and the salary, then the model will be able to give some predictions for each of the numbers of years of experience here. And you're going to see how the predictions will be close to the true results, which are the true salaries. That means that we will compare the true salaries with the predicted salaries. Okay, and now let's see what we need to change here for X and Y. So as a reminder, X is the matrix of features, that is the matrix of independent variable. Here, the independent variable is this variable here, the years experience, the number of years of experience, and then the dependent variable is the salary. So our matrix of features here, which is, taking the data set and removing the last column of the data set, that is this salary column with this -1 here, will contain only one column, which will be the number of years of experience. But then we need to change the index here for y, because remember in our data example in the data preprocessing part, the dependent variable was on the 4th column. So since indexes in Python start at 0, then it had index 3. But here you can see that the dependent variable is the 2nd column. And so since indexes in Python start at 0, that means that this column here has index 1. So here, since we need to put the index of the dependent variable column, then that means we need to put 1. And then we're all good. We're ready to create our matrix of features, which is here a matrix of only 1 column and our dependent variable vector. So let's do this. You'll see. I'll select this line and press Command and Control plus Enter to execute. Here it is. The matrix of features X is created. Let's have a look. X. So as I just told you, this matrix contains only 1 column. You can see here actually that it contains 30 lines in 1 column. So that's our matrix of independent variable. And now let's create our dependent variable vector. And now that we corrected the index here, it should be all fine. So let's select this and press Command or Control plus Enter to execute. Here it is. Let's have a look at Y. And here's Y. We can change the format again and replace this 3 by 0 to have the salaries in this format. That's better. And that's all our salaries, and this column is the dependent variable vector. And as you can see, we can clearly make the difference here between the matrix of features and the vector here, because as you can see, there is this 1 here that tells that this is a matrix that has 1 column, and here we don't have anything after the comma. That means that it's a vector. So you have to make the distinction between the fact that this X here is a matrix because it's the matrix of features, the matrix of independent variable, and Y here is a vector since it's the vector of the dependent variable. So let's click OK, and now we're all good. So now we're ready to move on to the next sub-step of the data preprocessing first step of our model, and this is to split the data set into the training set and the test set. So let's see, we have 30 observations. So a good split would be to have, for example, 20 observations in the training set and 10 observations in the test set. Let's pick that split, even if we recommend in general more like an 80-20% split. But here we're making a simple model, so we can select 20 observations to go to the training set and 10 to go to the test set. So that means that for the test size here, we need to input 1/3. So that way 1/3 of 30 equals 10 observations will go to the test set. And that's it, that's all we need to change. Now we're ready to make the split of the dataset into the training set and the test set. And remember, this random state parameter here, set to 0, is here so that we all get the same results, because there are some random factors in the algorithm. So it's better for the learning experience if we all have the same results. So let's select this, it's all ready now. Let's select the section and press Command and Control plus Enter to execute. And as you can see now, our training set composed of X-train and Y-train is created, and our test set composed of X-test and Y-test is created as well. So let's have a look at them. X-train, Y-train, X-test, and Y-test. Okay, so these two sets above are composing the training set because it contains X-train, the matrix of independent variable, and Y-train, the dependent variable vector for the training set. And below is the test set, composed of X-test, the matrix of independent variable for the test set, and Y-test, the dependent variable vector. And so what happens is that we are going to train our model on the training set here. That means that our model will learn the correlations between X-train here and Y-train so that it can later predict the results of the dependent variable, the salaries, based on these informations here. And then once our model is trained on the training set by having learned all the correlations between these two variables, we will test its performance, its power of prediction on the test set here. So that means that for each of the test set observations here, we will predict the corresponding salary, and then we will compare the predicted salary to the real salary, which are the salaries here. So you're going to see that in the next step, but that's the idea behind making a model, making any machine learning model. We are training the model on the training set. That means that our model learns on the training set, and then we're testing its performance on the test set. Okay, so let's click OK to close the windows here. And now let's move on to the next step. And actually, the next step is feature scaling. And as I mentioned in the data preprocessing part, most of the libraries that we'll use in Python as well as in R are going to take care of feature scaling for us. So that will be the case for simple linear regression. That will sometimes not be the case. I will let you find out the surprise. But for simple linear regression, we don't need to apply feature scaling. The library is going to take care of that for us. So we will leave this section in comment, and then that means we are ready to move on to the next step. Our data is well preprocessed now, and we are ready to move on to the next step, which will be to fit the simple linear regression algorithm to our training set. So thank you for watching this tutorial, and I look forward to starting to make this simple linear regression model in the next step. Until then, enjoy machine learning. Hello and welcome to this Python tutorial. In a previous tutorial, we took care of the data preprocessing step, which is a compulsory step anytime you want to make a machine learning model. So that's what we did in the first step. Now the data is all well preprocessed. We have our training set here with X-train and Y-train, and our test set composed of X-test and Y-test. And we didn't have to apply feature scaling. As you can see on X-train here, we have the numbers of years of experience as they were originally. And that's because the library that we're going to choose to build our simple linear regression model will take care of that for us. And speaking of library, that's what we're going to do in this tutorial, because we are going to fit the simple linear regression model to the training set. And to do this, we're going to use this specific library that will do the job for us, and you will see how easy it is to fit the simple linear regression model to the training set. So let's do this right now. The first thing that we need to do is obviously to import this specific library. And so we're going to import it from scikit-learn, which contains a great deal of libraries and tools to make machine learning models. And so the library that we're going to use for simple linear regression is the linear model library from scikit-learn. And then in this library, we are going to import a class, which is the linear regression class. And then what will happen is the following thing. We are going to create an object of the linear regression class, and this object will actually be the regressor, the simple linear regressor. And so we're going to call this object regressor simply because it's going to be the regressor that we will fit to the training set. And actually, in order to fit it to the training set, we will use something called a method, because the linear regression class contains several methods, and one of them is the fit method. And this method is like a tool, a function that will fit your regressor object that we will create to the training set. So let's write the code and everything will be all clear. So the first thing that we need to do is to import the linear regression class. So let's do this. So since we are importing this class from scikit-learn linear model library, we will first write from sklearn that linear underscore model, which is the name of the library. And so from this library, we are going to import the linear regression class. And the linear regression class is spelled this way, with capital L in linear and capital R in regression. No space. Here it is, that's your class, the linear regression class. And so now we are going to create an object of this linear regression class that we will call regressor. So here I'm writing regressor, and that's where I'm creating my object of the linear regression class. And to create an object of the class, here we need to call the linear regression class. And to call it, we simply write its name, linear regression, and then we write parentheses, because by doing this, this is like a function that will return an object of itself, which is actually the regressor. And actually, if we click here at the end of linear regression, and if we press Command plus I, that will inspect this class, and we will be able to get some info about this class. So let's do this. Let's press Command plus I, and here, as you can see in the object inspector, I have some information about the linear regression class. So the main information that we're mostly interested in are the parameters. But here, that's just to show you that we can get some information about the class and that there are some parameters to input. But these are not compulsory parameters to input, and therefore we will not input any parameters here. We are satisfied with this. With this, we can create a simple linear regression model. We don't need to input the parameters. So that's it. With this simple line, the regressor object is made, and now what we need to do is to fit it to the training set. And so as I told you, a class contains some methods, and one of these methods is the fit method, and that's the method we will use to fit the regressor object to our training set. And so to use this method, we need to first take the object, regressor. Then by adding a dot here, we can, as you can see, call the different methods of the linear regression class. These are all the methods, and so the method we want to choose is the fit method, because it's the method that will fit our regressor object to the training set. So let's press enter here, and now we're taking the fit method. And so now we need to add some parentheses, because we need to specify which data set we want to fit the regressor to. And of course it's a training set. And remember, the training set in Python is composed of xtrain and ytrain. So here we will need to specify both. And actually we can do the same here for fit. We can inspect it by pressing Command plus I. And as you can see, this gives the information about the fit method, and especially the parameters to input. And here you can see that the first parameter is x, which is the training data. And by training data here, they mean that it's the matrix of features of the training set. And the matrix of features of the training set is the matrix of the independent variable, that is xtrain. Because if we go to Variable Explorer here, you can see that xtrain contains the independent variable, and only the independent variable, and that's where we want to input for this x here. So that means that the first argument is xtrain. And then what is the second argument? It says that the second argument is y, and that y is the target values. So the target values is just another name for dependent variable, because these are the target values that we want to predict. And of course this has to be associated to xtrain here, because we are fitting our regressor to the training set. So y here is going to be the dependent variable vector of the training set, that is ytrain. So here for the second parameter we need to input y underscore train. And that's it. This line of code fits your regressor object, which is an object of the linear regression class, to the training set composed of xtrain and ytrain. And so now this code section is ready, so we are ready to select this and execute, and this will not only create our simple linear regressor, but also it will fit this regressor to our training data. That means that by executing this code section here, our model will already learn the correlations of our training set to learn how it can predict the dependent variable, which is the salary, based on the information of the independent variable, that is the number of years of experience. So now let's press Command or Control plus Enter to execute this code section here. And here we go. Our simple linear regressor is created and fitted to the training set. So if you want to compare it to machine learning, well, here the machine is the simple linear regression model, and learning is the fact that this simple linear regression machine learned on the training set here, composed of xtrain and ytrain. So that's what machine learning is. We created a machine, which is the regressor here, the simple linear regressor, and we made this machine learn on the training set to understand the correlations between the experience and the salary, so that this machine, based on its learning experience, can then predict the salary with respect to the experience. So that's what machine learning is about. This is the most simple machine learning model, and we just created it. Alright, so that's it for this tutorial. In this tutorial we created our simple linear regression machine, and in the next tutorial we will use this simple linear regressor to predict some new observations, and these new observations will be the test set observations. So I'll see you in the next tutorial, and until then, enjoy machine learning. Hello and welcome to this Python tutorial. In the two previous tutorials we did our two first steps of making the machine learning model. The first step was to pre-process the data to make it ready to build our machine learning model, that is our simple linear regression model. And actually the second step was to create this model. What we did is we imported the linear regression class from the linear model library. Then we created an object of this class, which is the simple linear regressor itself. And then, since any class contains methods, that is tools or functions, we used one of these methods, which is the fit method, which fitted our simple linear regressor object to the training set. And the fact that we fit it to the training set, what does that mean? That means that our simple linear regressor learned the correlations of the training set, that is, learned the correlations between the number of years of experience and the salary, to learn how it can predict the salaries based on the experience. And now that the simple linear regression, that is the machine itself, learned these correlations, we can see how it will predict some new observations, which will be the test set observations. And that's what we're going to do in this tutorial. We're going to see how our simple linear regression machine learned the correlations in a training set to see how it can predict the test set observations, which are new observations, because indeed our simple linear regression model didn't learn anything from the test set. So let's see how it can predict new observations. And to do this, we will create a vector of predicted values. That is, we will create a vector that will contain the predictions of the test set salaries, and we will put all these predicted salaries into a single vector that we will call ypred. So ypred, and this is going to be the same for all machine learning models that we will create, ypred is going to be the vector of predictions of the dependent variable. And in this particular example for simple linear regression, since the dependent variable is the salary, then that means that this vector will contain the predicted salaries for all the observations of our test set. So now let's create this vector of predictions. So here we'll add equal, and now we will take our regressor that we created and trained on the training set, and again we're going to use a method of the linear regression class. But this time it's not going to be the fit method, it's going to be the predict method. And the predict method, as you can guess, is a method that will make the predictions of the salaries of some observations. And therefore we will need to specify which observations we want to make the predictions, and so we will need to specify that we want to make the predictions of the test set. And so in this predict function we will input the test set, but you will see. So as always, when we want to use a method, we add a little dot here, and then we can choose the method here, as you can see. So before we used the fit method, and this time we're using the predict method. So I just pressed enter, and now we can input some parameter. So if we press Command I to inspect the predict method, we get this, and you can see that in the parameters it says that we need to input only one parameter, and that this parameter is x, and x is of course our matrix of features of new observations, and therefore it's going to be x test. And let's select this line because now it's ready. Our vector of predictions is ready to be built. Execute, and now we can see our ypred vector that actually appeared in the variables in Variable Explorer. So let's have a look. Here is ypred, and let's also open ytest to compare. Alright, so now what's very important to understand is the distinction between ytest and ypred. So it's very simple. Ytest is the real salaries of your 10 observations in a test set. That's the salaries those 10 employees here really have in the company. And then those salaries here in the ypred vector are the predicted salaries. So that's the salaries of these 10 employees predicted by our simple linear regression model. So in short, ytest contains the real salaries and ypred contains the predicted salaries. So now what's interesting to do is to compare the real salaries to the predicted salaries. So for example, let's take the first observation. So this real salary here and this predicted salary here correspond to the same employee. And we can see that this particular employee indexed by 0 has a $37,000 salary, and that's his real salary. And our model predicted that this employee has a $40,000 salary. So the predicted salary is not too far from the real salary, and that actually makes a good prediction. We can have less good prediction. For example, if we look at the 7th employee here, well, its real salary is $55,000, and our model predicted that this employee has a $64,000 salary, so it overestimated the salary. And you'll understand why it did that after when we look at the graphic results. You'll perfectly understand why, because you'll see that the simple linear regression is actually a straight line that is trying to be the closest as possible to the real observation points. So you will see why sometimes make some predictions that are far from the reality. But then it can also make some great predictions, and that's the case for the last one, because the last employee of the test set has a $101,000 salary, and our model predicted that this same employee has $100,000, well, almost $101,000 salary, so that's a very accurate prediction. Okay, so let's click OK now. That's the idea about the vector of predictions that we create here. And in the next tutorial, all this will get a lot more clear, because we will visualize the result, we will visualize what's happening between, the truth and the predictions. We will build a plot where we'll have our true observation points, that means our employee with their real salaries, and then we will plot a straight fitting line that is going to be the simple linear regression line, and on this line will actually be the predictions of our model for each of the employees. So I look forward to seeing you in the next tutorial to make this plot. Until then, enjoy machine learning! Hello and welcome to this Python tutorial. In the previous tutorials we did the first steps of making our simple linear regression model, and those included the data preprocessing step, then fitting simple linear regression to the training set, which is where our model learned the correlations to make the future predictions, and then speaking of predictions as the third step, we predicted the test set results, and now we are finally getting to the fun part, which is to visualize the training set and the test set results. So that means that we're going to plot our observation points as well as the simple linear regression line to see how there is this linear dependency and to see how the predictions of the simple linear model can be close to the real observations. So let's do this, let's plot these graphs and let's interpret the results. Okay, so generally to plot a graph in Python we're going to use this matplotlib pyplot library that we imported as an essential library in the preprocessing step. So it's already imported, that's great, we're ready to start plotting our graphs. So the first thing that we're going to do is to plot the real observation points, that is the employees of the company, characterized by their number of years experience and their salary. That means that on the x-axis we will have the number of years of experience, and on the y-axis we'll have the salary. So let's do this. It's actually quite simple. We need to use plt.scatter, which is a function of pyplot that will make a scatter plot of the observation points of your dataset. So you'll see it's actually quite simple. We just need to type plt.scatter. Then in parentheses we first need to input the x coordinate of your observation point, so that's xtrain, because first we're starting with the training set. Xtrain, so that's actually the x coordinate of our observation points, because xtrain contains the number of years of experience, as you can see. These are the number of years of experience in xtrain. And now what will be the y coordinate? Well, the y coordinate will be the real salaries that the employees have in the company, and of course this is the salaries contained in the y-train vector. If we look at y-train here, these are the real salaries of our observation points, that is of our employees in the company. So okay, that will be y-train. And then since we'll plot the observation points and also the regression line, it would be better to colorize in different colors those two entities, like the observation points in one color and the regression line in another color. So that's as you prefer. Generally what I like to choose is to colorize the observation points in red and the regression line in blue. So here I'll just choose color equals red. Alright, and that will plot all the observation points, the real values. And now what we're going to do is to plot the regression line, that is the predictions. So here we're not going to choose plt.scatter because we're not making a scatter plot of the points. We will use simply plt.plot. And then as usual in plt.plot we will first enter the x coordinate of the points in the regression line and the y coordinate. So the x coordinate will be xtrain as well, because to plot a line we just need some x coordinates of the line, and then we'll specify what the y coordinates are. And speaking of y coordinates, what do you think the y coordinates of this regression line will be? Well, it will be the predictions of the xtrain numbers of years of experience, and the predictions of these numbers of years of experience in the training set in xtrain are the predicted salaries of the xtrain observations. So then be careful, it's not ypred, because ypred are the predicted salaries of the test set observations. Here we have test set. But what we only need to do is to just take this, copy this, and paste it here. And here we'll just need to replace xtest by xtrain, because we want the predictions of the training set and not the test set. Because here, we want to compare the real salaries to the predicted salaries, but based on the same observations. That is, the observations of the training set. Okay, so then we have our x coordinate and our y coordinate of the regression line. And now what do we need? A color. Yes, because we want to make the distinction between the observation points above and our regression line. So since we chose red for the observation points, here we'll choose blue. Or you can choose whatever you want. That's just my personal preference, but you're welcome to try something different. And here it is. This second line plots the simple linear regression fitting line to our training set. Okay, now we'll just improve our plot by giving a title, a label of the x-axis, a label to the y-axis, and it will be ready. So let's do this. Let's add a title. It's plt.title. Let's give salary vs experience, because we want to see the relationship between the salary and the experience. And here let's just add training set in parentheses to specify that we're plotting the training set results, because then we'll do the same for the test set results. So just to make the distinction. And that's it for the title. Great, now let's add a label to the x-axis. So to do this, we just need to add the command plt.xlabel. And then let's call our x-axis years of experience, because on the x-axis are the numbers of years of experience. So years of experience. Here it is. Great. And now same for the y-axis. So this time it's going to be plt.ylabel. And then parenthesis salary. All right. Great. And then we just need to add a final line. It's plt.show with parentheses, and that's to specify that it's the end of the graph and that we're ready to plot it. Okay, so now it should be good. We have our observation points thanks to plt.scatter. We have our regression line thanks to plt.plot. We have a title, labels to our axis, so it should be all fine. Let's try. Let's try to select this and execute. Press Command and Control plus Enter to execute. And here is our graph. Great. Let's enlarge this. Alright. So, okay, the first really important distinction to understand is that we need to make the distinction between the real values and the predicted values. So the real values are our red observation points, all these red points here. These contain the real values of our employees, that is, okay, their years of experience, but then their real salary, the salary they really have in the company. And then the predicted values are on this blue simple linear regression line. And by predicted values, I mean the predicted salaries, which are the projections of the points of this line to the y-axis. So for example, if we take this observation point here, that corresponds to an employee that has 4 years of experience and a salary about 55,000. So that's its real salary. But then to get the predicted salary of this employee, we need to first project this point on the regression line and then project again to the y-axis to get the predicted salary, which is then 60,000. So for this observation point, the real value for its salary is 55,000 and the predicted value for its salary is 60,000. So that's the first really important distinction to make. Now, what's interesting to see is that there is clearly a linear dependency between the salary and the years of experience, because as we can see, our regression line is approaching quite well all our observation points. You know, if we had some points everywhere, then our regression model could fit a straight line, but it would be far from our observation points. But here, since it's approaching quite well the points, then that means that there is linear dependency, and that's why we could fit a good simple linear regression model that gives good predictions. And speaking of predictions, we have some accurate predictions. For example, this one, you can see that the real salary is close to the predicted salary. This one too. This one is a very accurate prediction. The prediction is almost perfect. and this one as well. And then of course we have some less accurate predictions because this is not a 100% linear dependency. So of course, for example, this real salary here is further from the predicted salary, which is here. So here, as you can see, that's the predicted salary for this particular employee, and that's the real salary. And same for this employee, and this one as well, this one as well. And now the third thing that is actually important and that we have to keep in mind each time we make a model is that these are the observations of the training set. So these are the results of our simple linear regression model, but which was trained on all these red points here, on all these red observation points here. So let's see how this simple linear regression blue line can approach new observations. And these new observations will actually be the test set observations. These are new observations because our model didn't learn on these test set observations. So what we will do next is we will plot the same kind of graph. We will keep this blue regression line because this is the regression line that was trained on the training set, so we don't want to change that. However, we will plot some new red points here because here these are the training set observation points, and we will plot in the second graph the test set observation points. So let's do this and let's see how our simple linear regression line can predict some new observations. So what we'll do is we'll copy this actually and paste it here because you'll see that we will only have a few things to change. Okay, so first let's change the section title here and specify that we're now visualizing the test set results. Okay, and here let's specify also in the title of the plot that we're now plotting the test set results. Great. And now what do we need to choose? Okay, so in the first line is plt.scatter that plots our observation points. And now since we are interested in looking at the observation points of the test set, here it won't be x-train and y-train, it will be x-test and y-test, because x-test and y-test are the coordinates of the observation points of the test set. And then, something very important to understand here. Do you think that in the second line, plt.plot, do you think we need to change x-train here and here by x-test? And the answer is no, because our regressor is already trained on the training set, so whether we keep here the training set or replace by test set, we will obtain the same simple linear regression line. Indeed, if we replaced here x-train by x-test, we would just build some new points of the same regression line corresponding to the new predictions of the test set observation points, because when we trained our simple linear regressor on the training set, we obtained one unique model equation, which is the simple linear equation itself. And therefore, whether we build the regression line here by predicting the training set points or the test set points, well, since these predictions result from the same unique simple linear equation, we will get the same regression line. So actually this is ready now. We are ready to plot the test set results. So let's do this. I'll select this and press Command and Control plus Enter to execute. And here are the test set results. So let's enlarge this. Okay, so these are the test set results. So be careful, this blue regression line is the blue regression line that we had in our previous plot in the training set results. So that's the same line because that's our simple linear regression model trained on the training set. But then these red points here are new points. These are the observation points of the test set, whereas before it was the observation points of the training set. So it's important to understand all this. And now let's interpret and let's give the final verdict. Well, this is actually really good because these are new observations and our simple linear regression model is making some very good job at predicting those new employee salaries. Because for example, if we take this one, it's clearly on the simple linear regression line. So the predicted salary is the same as the real salary because the red point is on the line. Same for this one, very accurate prediction, and same for this one, and this one as well. And of course, since there's no 100% linear dependency between the salary and the years of experience, there is of course some less accurate predictions like these two and this one and maybe a little bit this one. But overall that's great. We made a good simple linear regression model that is perfectly able to predict new observations thanks to this linear dependency between the salary and their years of experience. Alright, so thank you for watching these tutorials and congratulations for making your very first machine learning model. So keep in mind, the machine here is the simple linear regression model, and learning means that we trained this simple linear regression machine model on the training set. That means that it learned the correlations of the training set to be able to make some future predictions. And you know, so these are the predictions of the test sets, but we could make some new predictions with some new employees having other years of experience, and that would give us some great prediction of its salary, even if it was not in the original dataset observation point. So thank you very much for watching this tutorial. I hope you enjoyed what you learned, and I look forward to seeing you in the next section. Well, first we'll do the same simple linear regression model on R, and then we'll move on to the next level, which will be the multiple linear regression model, where we'll add some new dimensions, because this time there will not only be one independent variable, there will be several independent variables, and we'll learn how to deal with that. So thank you very much, and until next time, enjoy machine learning. Hello and welcome to this R tutorial. So in the following tutorials, we're going to implement the simple linear regression model on R. So it's going to be the same steps as in Python, and let's start with the first step. So the first step is to actually set the working directory. As you can see right now, I'm on my desktop. So I'm going to go to my machine learning AZ folder, part 2 regression, and then section 4 simple linear regression. And here we are. That's the folder we want to set as working directory. Make sure that it contains your salary data.csv file. That's the data on which we will build our simple linear regression model. So make sure it is here. And now to set this folder as working directory, you just need to click on this more button here and then click on set as working directory. And that's it. That's done. Now we're ready to start. We are ready to start with the real first step of making a machine learning model, which is the data preprocessing step. So we're going to use, of course, the data preprocessing template that we made in part 1. So I'm just going to copy the template here, only this, copy, and then paste it here. All right. And now we just need to change a few things to adapt it to our data set. So of course we will need to change the name of the data set here. It is not data.csv, but salary underscore data. Okay, so then I'm going to select this to have a look at the data set. Here we go, let's have a look. Here's the data set. Okay, so just to remind what this data set is about, this data set contains some information of employees in a company. And these two informations are the number of years of experience the employee has and the salary. So we are trying to understand if there is a correlation between the salary and the number of years of experience. And mostly we're trying to see if it's a linear correlation. That means if there is a linear dependency between these two variables. And so what we need to understand, that the first reflex that we must have when we make a model, is that we must understand which is the independent variable and which is the dependent variable. So the independent variable is the number of years of experience, and the dependent variable is the salary. And so what happens is that we are trying to predict the dependent variable salary based on the information of the independent variable years of experience. Okay, so that's the data set, and now let's continue with our model. So let's go back to simple linear regression here, and we don't need to specify any column of interest. We have all we need, so we won't use this line here. Okay, now we are ready to split the data set into the training set and the test set. So we perhaps need to change the split ratio. Let's see, the data set contains 30 observations, so what would be a good split ratio? It's really as you prefer. I know that I told you that a good split ratio is 75%, but just for the sake of beauty, let's take 20 observations in a training set and 10 observations in a test set. So that would be that the split ratio would be 2/3. Okay, and of course, let's not forget to change the name of the dependent variable, because this was the name of the data in the template. And now let's see what the name is. The name is salary. So here, you know, that's the name of the dependent variable. So we need to change purchased into salary. Now I think it's ready. We're ready to split the data set into the training set and the test set. So let's do it and let's see what happens. Here we go. It worked perfectly. So now let's have a look at the training set and the test set. Okay, the training set contains the 20 observations generated from the split, and in the test set we have our 10 observations. So we are going to train our simple linear regression model on the training set. That means that our model is going to learn the correlations between the number of years of experience and the salary in this set here, in the training set. And then later we will test its performance, its power of prediction, on the test set. So let's continue. The last step of the data preprocessing is feature scaling, but the simple linear regression package that we're going to use here in R takes care of this, so we won't need to apply feature scaling manually, so we will be fine with that, and actually the data preprocessing phase is ready. So awesome, we are ready to start building the linear regression model. We're going to do that in the next tutorial, so I can't wait to see you there, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in the previous tutorial we prepared our data correctly, so that now we are ready to fit our simple linear regression to our dataset without any issues. So we're going to do that right now, and as usual we're going to use the simplest way, which is to take the lm function. So we're going to do that right now. We're going to call a new variable regressor, and that's going to be the simple linear regressor itself. Then equals, and then that's where we use the lm function. So let's just type lm here, and then let's press F1 to see the info of this function, and especially the arguments. So let's see, the first argument we have to input is formula, so let's input it, formula, and according to you, what is it going to be? Well, this is going to be the dependent variable expressed as a linear combination of the independent variable. So here it's very simple, since we only have one dependent variable and one independent variable, we just need to type formula equals salary, then alt plus n, here you go, and then we put the independent variable, which is years experience. So what does this notation mean? That means that the salary is proportional to years experience. Okay, so that's it for the first argument. That's the formula we need to input, and that's actually the simple linear regression formula. And then we need to add a second argument, which is, let's see, the data. Okay, and that's normal. That's because we have to specify to R on which data we want to train our simple linear regression model. And of course, this data is the training set, because the training set is the set on which you build your model. Okay, so that's it. Actually, I know there are some other arguments, but these are optional arguments that we don't really need here. So we will just use these two, formula and data. Okay, so that's it. The regressor will be ready once we select it and execute it. So let's do this right now. And let's press Command and Control plus Enter to execute. Here we go. Now the regressor is ready. As you can see, it just appeared here. If you want to have some info about this regressor, then the best way to do it is to, go here in the console and type summary regressor, because the name of our regressor is regressor. Then type enter, and then you have some very good information about your simple linear model. For example, okay, so let's see. Let's just put that up. Right. So first it tells you what the formula is. Okay, so it's the salary being proportional to the number of years of experience, and that the model is built on the training set. Then you have some info about the residuals. We won't be talking about this now, but the really important section is this one, coefficients, because not only it tells the value of your coefficients in the simple linear regression equation, but also it tells you the statistical significance of your coefficients. And here we observe 3 stars here. That means the years experience independent variable is highly statistically significant, because you can either have no star or 1 star, 2 stars or 3 stars. No star means that there is no statistical significance, and 3 stars means that there is a high statistical significance. So that's the first info, that's the first hint of what is going to happen, because we already know by looking at this that there will be a strong linear relationship between the salary and the number of years of experience. And the other info here is the p-value, and the p-value is another indicator of the statistical significance, because the lower the p-value is, the more significant your independent variable is going to be. That is, the more impact, the more effect your independent variable is going to have on the dependent variable. And Usually a good threshold for the p-value is 5%, which means that when we are below 5%, the independent variable is highly significant, and when we are over 5%, that means that it's less significant. And here, as you can see, the p-value is 1.5210 at the power of minus 14, which means that it's a very, very, very small p-value. So that means that this independent variable years of experience is highly statistically significant and has high impact and high effect on the formula dependent variable. So that's very important information. Get the Reflex to look at these by, typing summary regressor, because this is really important, especially when you want to try out several potential independent variables. You need to look at their statistical significance to choose them. And then you have some informations of your model globally, which we will be talking about at the end of this part 1 regression, when we'll be talking about ways to evaluate your model. When here, as you can see, you have the multiple R squared that Kirill will talk to you about, and the adjusted R squared if you have several models with several teams of independent variables. Then that's the adjusted R squared you must choose to choose the best model. Alright, so that was just a parenthesis to give you this very important trick to know in R and learn how to evaluate your model already. So actually we are done fitting the simple linear regression to our data set, our training set, and in the next tutorial we are going to be predicting the test set results to finally see how our simple linear regression behaves on a new set, on some new observations. Okay, so that's the end of this tutorial. I look forward to seeing you in the next one, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So in the previous tutorials we prepared our data set, then we fitted the simple linear regression model to our training set, and now we're going to predict the test set results, because we trained our model on the training set and we want to see how it can predict new observations. So to do this, we're going to create our vector of prediction ypred. I'm calling it ypred because this is a vector of prediction, that is the vector that will contain the predicted values of the test set observations, and we are going to use the predict function. So I'm going to write that here. So that's the predict function, parenthesis. And in this predict function, it's really simple. We will just need to input two arguments. The first one is our regressor. So that's the simple linear regressor. And then, comma, and then the second argument is new data. So that's the name of the argument, but then this new data is the data that contains the new observations that we want to predict the result, and so obviously that's the test set. And actually that is ready. We are ready to build our vector of predictions. I will just remind what this is going to do. Here we have a test set. This is the column of the number of years of experience. So what will happen is that our simple linear regression will predict for each of these test set observations the salary. So it won't be the same salary here because these are the real salaries, the salaries that actually exist in real life. But since we saw that there is a strong linear dependency between the years of experience and the salary, the predictions returned by our simple linear regression model should be close to this salary. Anyway, we're going to see that in the final step of this simple linear regression model, because we will visualize on a graph all the results, but so far it's just to explain you what we're expecting. So let's go back to our model and let's select this, Command or Control plus Enter to execute, and here we go. The vector of prediction is now created, so let's have a look at it. We're gonna type ypred here in the console, and here it is. These are all the salary predictions for our 10 observations in our test set. Okay, so for example, let's have a look at the first observation. The real value, the real salary of the first employee of the test set was $46,205, and let's see what our model predicted. It predicted $37,000. So that's not too close. But then if we look at the second observation, which is the fourth employee, let's call it the fourth employee, his real salary is $43,525, and our model predicted $44,322, which is this time much closer. Okay, so that's it with this tutorial. And now the next tutorial is my favorite part, the part where we visually see what everything that we've been making, that is, we will be visualizing on a graph the training set results and the test set results. So we will make two graphs, a first graph showing the predictions of the training set observations and a second graph showing the predictions of the test set observations, and we will see how the simple linear regression line approach the real observations. So I look forward to seeing you in the next tutorial, and until then, enjoy machine learning. Hello and welcome to this R tutorial. So now it's time for the fun part. I can't wait to show you the training set results and the test set results. So let's start to build the graphs. So the first thing we're going to do is to import the ggplot2 library, which is a very good way of plotting something in R. So I'm going to import it. But before importing this library, there might be some of you who are starting R for the first time. So if we go to our packages here, you can see that the ggplot2 library is here on my R Studio, but it might not be the case for you and that would mean that the ggplot2 library is not installed on your R. So just for those of you for which it's the case, I'm going to install ggplot2 library. So we have to use this command install packages here, and then in parentheses we add ggplot2, ggplot2. Then we select this, press Command or Control plus Enter to execute, and here right now you can see it's installing the library, and that's done. So that's the message you should be obtaining when you install a package. Now it should be appearing in your library, so mine is here, and we are ready to start plotting the graph. I'm just going to put that in comment, so Command Shift plus C, now it's in comment because once it's installed we don't need to install it again. Okay, so now let's start to plot our training set results graph. So first thing we need to do, as you can see, the ggplot2 library is not selected here, so we will need to select it, but we want to automate all this if we want to use simple linear regression on another dataset. So we will just type here library, then in parentheses the name of the library, not in quote actually, ggplot2, and as you can see, if I select this line and execute, here you see that it's not selected, and if I execute, it's selected. Here we just have a suggestion to type suppress package startup messages to eliminate package startup messages. Well, that's not very important. You can execute that if you don't want the package startup messages, but that's okay. So I'm just going to enlarge this. Okay, and now like for this course, the approach we will be taking to build this graph with ggplot2 is going to be a step-by-step approach, because we are first going to plot all the observation points in the training set, then we're going to plot the regression line, and then we're going to add a title, and then a label to the x-axis and a label to the y-axis. So you know it's going to be step by step. First the observation points, then the regression line, then the title, then the labels. Okay, so let's start with the observation points. So generally to introduce a plot in ggplot, we start by typing ggplot parentheses, alright? And then that's when we start to build step by step the little components of our graph. And since we're adding each component one by one, we're going to separate each of these components by a plus. So let's go for the first component, plus here, I will press enter, and here we go for the first component. So the first component are the observation points, so very intuitively we are going to write geom_point, alright? So we are going to use this function of ggplot to scatter plot all our observation points of the training set. So the first thing that we need to do is to precise which are going to be the x-axis and the y-axis, and that's in the aesthetic function, which we call AES. So that's the function that will take as input the x variables and the y variables. So the x variables is our years experience variable, that means the number of years of experience. That's what we want to have in the x-axis. And the y variable will be our salaries, but the real ones, not the predicted ones yet. So therefore, we're going to add in parentheses x equals, and then we're going to put all our years of experience. But be careful, we want to take the years of experience of the observations in a training set. So here we'll just have to specify training set $, and then years experience. So that means that we are taking the years experience values of the observations in the training set. Okay? And now same for y. And here we do the same, only with the salaries, which is here. Okay, and that plots all your observation points, the real ones, in the plot. Okay, so we could stop here, but we would like to add a color because we will want to make the distinction between the observation points and the regression line to, make a nice plot. So comma here, and then I'm gonna press enter to add a new argument of geom_point, because this can be a little confusing here. We have a comma here and a comma here. This comma here is just to separate the x and the y in the aesthetic function, and this comma here is to separate the first argument and the second argument of the geom_point function. So the second argument is color, and let's pick red. I usually like to have my observation points in red, but that's just my taste. If you have some other taste, you're welcome to choose your favorite color for the observation points. Okay, so that's it for the geom_point. With this geom_point part here, we are plotting all the observation points of our training set. And now let's add the following component, which is our regression line. So here we add a little plus and then enter. So to plot the observation points, we used geom_point, and now very intuitively, to plot the regression line, we're going to use geom_line. Alright, so pretty easy to remember. And then in this line, same as for the point, we're going to take the x-coordinate and the y-coordinate of our regression line. So let's see, first we need to take the function aesthetic, AES, parenthesis, and that's where we put the x and the y. So, in your opinion, what is going to be the x? Well, the x is going to be the year's experience of the training set, because we want to have the predictions of the salaries for the observations in the training set. So in the x-axis we need to have the number of years of experience of the training set observations. So here I'm just going to copy this there and paste it here. But now, what is going to be the y? It's not going to be training set salary, obviously, because we don't want to take the real salaries. Now we want to take the predicted salaries. So in order to take the predicted salaries, we will very simply use again this predict function. We cannot use again ypred here because ypred is the predicted salaries of the test set observations, but here we want to get the training set predicted salaries. So we will copy this, predict, to take the predictions of the training set salaries, and therefore in new data here we need to replace test set by training set. And now it's good. Now this geom_line function here will plot all the predicted salaries of the training set observations. And so for each employee with the same number of years of experience, because here we have the same x, we're going to have both the real salaries, the salaries they actually have in the company, and the salaries predicted by our simple linear regression model for the same employees. Okay, so it's ready, the line is ready, but as for the observation points, we will just add a color, and then that means that we need to put a comma here and press enter. And that's where we put the second argument, which is going to be the color, and this time we will pick a blue color. So again, that's just my taste. You're welcome to use some other colors if you prefer. Okay, so now our plot is almost ready. We have all the observation points of the training set. We have the regression line. And so now we could plot the graph now, but if we want to have a nice graph that we want to present to people like managers or clients or even your friends, it's always better to add a little title and some labels on the axis. So let's do this, plus here, and GG, so this time it's not geom, it's GG because it's not a geometrical thing, GG title, parenthesis, quotes, because we have to put the title of our plot in quotes, and here we're going to give the following title, salary vs experience. And we are going to specify that it's the training set, because then we will do the same for the test set. And close the parenthesis, and that's it. So perfect, that's our title. And now let's just add a name of the x-axis. So to do this we use the xlab, and in parenthesis we will say that the name of our x-axis is going to be years of experience. Okay, and then plus, and then same for our y-axis, and obviously it's going to be ylab, and here we'll choose salary. Very simply. Okay, and our graph is ready to be plotted. So I'm going to select all this, and now press Command or Control plus Enter to execute. And here is our beautiful graph. So that's the training set results with the real training set observations with the real salaries in red and the regression line in blue. So let's zoom this graph and let's give an interpretation. Alright, so this is our training set results. So we can clearly make the distinction between the real observations, which are the red points. So these are the real salaries of the employees in the company. And this blue straight line here is our linear regression model. So that's the prediction. That means that, for example, if we take this employee here, well, we can see that his number of years of experience is a little more than 5 years of experience. His real salary is about $65,000, but our model predicted for this particular employee this result here. That means he predicted that this employee has a salary of a little less than $75,000. Okay, so that's a real important distinction to understand. This is the real value and this is the predicted value of the model. And to get the predicted salary, you need to project this point of the line here onto the salary axis, which gives us a predicted salary of a little less than $75,000. Alright, so that's the results of the training set. These are quite good results, but that's because we trained our linear regression models on the training set. And now let's see how our simple linear regression model can predict new observations, that is, new observations of the test set. So I'm going to close that. Okay, and now let's do the same for the test sets to see if our simple linear regression can make some good predictions on new observations. So the test set observations on which our model wasn't built. So as usual, we want to be efficient, and so we're going to copy all this, copy, and paste it here. Okay, so let's replace all the training set here by test set. Okay, here as well, training set, test set, that's the test set results. Okay, so now we must be careful with something. Let's see if we have to replace all the training sets. So in the first component of ggplot, that is when we plot all the observation points, the real observations, here we have training set years experience and training set salary. In your opinion, do we need to change training set here by test set? Yes, of course, because this time we want to have the observation points of the test set. So we want to take the years experience here of the test set observations and the salaries of the test set observations. And here we will replace training set by test set. Okay, but now in geom_line, so that is the component that builds the regression line, do we need to replace training set by test set here? You know, training set here and training set here? Do we need to replace those two training sets by test set? Well, the answer is actually, of course, no, because our regressor is already trained on the training set, so whether we keep here the training set or replace by test set, we will obtain the same simple linear regression line. Indeed, if we replaced here training set by test set, we would just build some new points of the same regression line corresponding to the new predictions of the test set observation points, because when we trained our simple linear regressor on the training set, we obtained one unique model equation, which is the simple linear equation itself. And therefore, whether we build the regression line here by predicting the training set points or the test set points, well, since these predictions result from the same unique simple linear equation, we will get the same regression line. Okay, now, so that means that now we're ready. Okay, test set here, and training set here. We're all good. We are ready to plot the test set results to find out how our simple linear regression behaves on new observations. So let's do this. Press Command and Control plus Enter to execute. And here we go. So as you can see, as I was telling you, if we go back to the training set here, you can see that only the red points change, you see, and the blue regression line doesn't change. You see, it's the same. Here, only the red points change. So here, that's the training set observation points with the model built on the training set, And here that's the test set observations with the same regression line built on the training set. Okay, so now let's zoom on the test set plot and give some interpretation. Okay, so the test set results are actually not bad. We can see that we have some very good predictions here. For example, for this employee, this employee, this employee, and this one as well. Because as you can see, the real value is close to the prediction, which is on the blue regression line. So since these are new observations on which our simple linear regression model didn't learn any correlation, that's actually quite a good job to find, predictions so close to the real value. And of course, there are some predictions that are further from the real value, but that's because there is not 100% linear dependency between the salary and the years of experience. But for sure, there is a certain linear dependency. Alright, so thank you for watching this tutorial about simple linear regression. In the next section, we will find out about a new type of linear regression, which is going to be the multiple linear regression, meaning that instead of having only one independent variable, we'll have several independent variables that will predict a single dependent variable. So there will be a new business problem, and I can't wait to solve it with you using multiple linear regression. I'll see you in the next section, and until then, enjoy machine learning!
Secondly, we will discuss about the multiple linear regression and how to do it in practical way.
Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for the section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout the section as well. And you'll also need the machine learning template folder, which you're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning. Alright, so multiple linear regression dataset. Let's get straight into it. This one's going to be fun. 50 startups. This is going to be a venture capitalist fund challenge. All right. So what do we have here? We've only got 5 columns, but the real interesting thing about this dataset, this is like a very realistic, lifelike business challenge. So you've got 50 companies here, 50 companies in total, and what they have is they have some extracts from their profit and loss statements, from their income reports. So how much did the company in this given financial year that you're analyzing it for, how much in that year did it spend on research and development? How much did it spend on administration, like paying employees, paying executives and so on? And how much did it spend on marketing? So those are the three major operational spends, I guess, and which state it works in. And finally, what is the profit? What was the profit of that company for that financial year? And the challenge here is, this is a dataset, it's totally anonymized, so we don't know the companies, and also there's only 50 companies. So there's a venture capitalist fund that has hired you as a data scientist to analyze these 50 companies, or analyze this dataset and create a model that will tell the venture capitalist fund which types of companies it is most interested in investing, and their main criteria is the profit. So profit is their dependent variable, the most important variable for them, and these are all independent variables. So you have to create a model which will tell you about profit based on R&D spend, administration, marketing spend, and state. And bear in mind that the venture capitalist fund is not looking to invest in these 50 companies per se. It's not just giving you a data set and then, like, obviously then they would invest in this one because it's got the highest profit. But what they're looking for is, this is a sample, and they want to understand, for instance, where companies perform better in New York or California, all other things held equal, or which companies perform better if you hold these columns equal, right? Will a company that spends more on marketing perform better, or a company that spends less on marketing? Also, they want to understand, the main thing probably they want to understand is when they assess companies, do they look for companies that spend more on R&D spend, or on research and development, or companies that spend more on marketing? So which of these two spends yields better results of profit, brings more results of profit? And based on your model that you'll create, they'll set up a set of guidelines for their own venture capitalist fund, and they'll be like, okay, so we're most interested in companies, this is just an example, that work in New York, that operate in New York, and that have a very low administration spend and a very high R&D spend, so the R&D spend has to be much higher than administration and marketing spend, something like that. So basically you're helping them create a model based off of this sample that will allow them to assess where and into which companies they want to invest to achieve their goal of maximizing profit. So there you go. It's already not an obvious data set. It's got many variables, got many records. You can't just tell off the top of your head. You probably can see that they're ordered by profit here, right? But there is kind of a mix all over the place. So let's get into this. It's going to be a fun and exciting section. Multiple linear regression. Same thing, but many variables. So B0, one constant, and then many combinations or many pairs of B and X, and it can go up to quite a lot. Depends on how many regressors you have. Here, once again, you got a dependent variable, Y, so something you're explaining, but this time the difference is that you think there might be a few causations to it. So in the case of salary, for instance, it could be how much years of experience you've done, how many other courses you've done, how much how much time you spend at work, or things like that, or how valuable, how much money you make for the company in terms of a student and his grade. So if your dependent variable is what grade does the student get, then in the independent variables could be how much the student has studied for the exam, maybe how much he has slept before the exam, how many lectures he has attended throughout the course, and things like that. The constant is still there, and also you got the coefficients. Before we dive into this section, I wanted to give you a quick heads up that there's a caveat around everything that we're doing with linear regressions. Linear regressions have assumptions, and the assumptions are listed below: linearity, homoscedasticity, multivariate normality, independence of errors, and lack of multicollinearity. And before building a linear regression model, you need to check that these assumptions are true. And then you can only proceed and be sure that you're building a good linear regression model. Well, in this section, we won't be focusing on that. We won't be focusing on the assumptions of linear regressions in this section of the course. But if you ever do need to build a linear regression, then make sure that you don't just blindly follow the steps that I present to you in this section of the course, but you do need to go back to the assumptions of the linear regression and research them and make sure that they are correct when you're building your linear regression. Today we're talking about dummy variables. So basically the information that we have is the profit of each company or of each startup, then the R&D spend, the admin spend, the marketing spend. So those three are expenses that the company incurred, and then the state in which it operates, either New York or California. The challenge that we're faced with is that the venture capitalist fund wants to see if there's any correlations between profit and the amounts that have been spent on different expenses, R&D, admin, and marketing, and also in which state the company operates. So is there a correlation between profit and all of these variables, and how would you go about creating a model to understand how knowing R&D spend, admin, and marketing and state to predict profit. And so therefore, profit is our dependent variable, and the rest, the blue ones, are all independent variables. And what we need to do is build a linear regression. So let's go ahead and get started. As we would with a multiple linear regression, we would start by saying y, which is profit, is equal to what? What is it equal to? Well, first of all, there's a constant. In this case, it's B0, and I've put it under the profit column just because I needed to fit it somewhere. And then we would start adding on these variables into our equation. So then we've got the B1 coefficient times the X1 variable, which is R&D spend in this case, and X1 is actually the amount, the dollar amount that you see in the R&D column. Then you've got the admin variable, which is X2. It's got a coefficient of B2, once again admin, so in this case X2 is going to be the dollar amount you see in the admin column. Then you've got the marketing spend, X3, which will be the dollar amount you see in the marketing column. And then you've got the state variable, and here when we get here we're questioning what should we place in our equation for the state column, because we don't actually have a number, we don't have a dollar value or any other type of number to add into our equation. We can't just add a word into our equation. And the thing here is that state is actually a categorical variable. So we talked about types of variables before, and we understood that there's categorical variables and there's numeric variables. Well, in this case, state is a categorical variable, and therefore we can't add it to our equation. We need to do something about this situation. And the approach that you need to take when you face categorical variables in regression models is you need to create dummy variables. Let's see how we can do that. First, you need to go through your column and find all the different categories you have. So in this case, we have 2 categories. So for every single category that you found, you need to create a new column. For New York, we're going to create a column called New York, and for California, we're going to create a column California. So we're kind of expanding our data set and adding some additional columns into it. And how do we populate the columns? So this is the fun part. To populate these columns, let's start with the New York column. You need to find all of your rows where state actually says New York, and you need to, for those rows, you need to put a 1 in the New York column. And then in California, for all the rows that say California, basically for all the rows that don't say New York, whatever else they say, you just put a 0. And then for California, for the column California, you do the same thing. Wherever a row says California in the state column, you place a 1 in the California column. And for any other values in the state column, you place a 0 in the California column. And so you end up with a data set like this, and these 2 new columns are called dummy variables. And building your regression model from here is very simple. All you have to do is use the New York column, and you're going to be using it instead of state, so you're not going to be using state anymore. And basically you add a variable which is B4 times D1, and D1 in this case is your dummy variable for New York. and you don't use the California column either. So as you can see here, all of the information in our data is preserved if we just stick to the one New York column, because you can tell right away if D1 is a 1, then it's a company that operates in New York. If D1 is a 0, it's a company that operates in California. So we didn't lose any information by including only the New York column. And we will actually talk more about why you should never include all of your dummy variable columns in your regression model. We'll talk more about that in the next tutorial when we're talking about the dummy variable trap. But for now, I would like to discuss two things. So first of all, the New York column, or all of the dummy variables, they work as switches. In this case, let's look at the New York column, which we're including in our regression. It works like a light switch. So if it's a 1, then you know that this company is in New York. If it's a 0, so off in this case, in the case of the picture, then you know that the company doesn't work in New York. Option. So the dummy variables work like light switches, and that's why they're 1s and 0s, and they don't need any other values in them. And the second thing is that when you look at this approach, it might seem biased. So we are including a variable for New York, and there's a coefficient for New York. So we basically have this benefit of having a coefficient in our equation for New York, which is B4. But for California, there's no coefficient, because when D1 is 0, that whole last part of the equation becomes 0, and there's no benefit of a coefficient in our equation for California. And might seem biased at first, but in reality that's not the case, because the way regression models work is that they will take by default that state, or that variable, that dummy variable that you have not included. It will become the default situation for this regression model. So basically what that means is that the coefficient for California is going to be included in the constant in B0, and by default, when D1 is equal to 0, this whole equation will turn into an equation. You can think of it as it will turn into an equation for California. But then when D1 becomes 1, you're adding B4, which is, once again, like, this is a very basic explanation, but you're adding a coefficient which is the difference between New York and California. So basically you're altering from California to New York by flipping this light switch. If it's on off, then kind of default state, and the whole equation is working for California. If it's on, then by adding that B4, you're altering the equation from the default state of California to New York. So that's a intuitive way to think of dummy variables, so there's nothing wrong with the fact that we're only including 1. And once again, in the next tutorial, we'll talk more about why it is a bad idea to ever include both dummy variables. I look forward to seeing you next time. Until then, happy analyzing. Dummy variable trap. Last time we learned how to create dummy variables to replace our categorical predictor state in the model. We also discussed that you can never include both dummy variables at the same time. In our example, we omitted the California dummy. Now, why is that? What will happen if we include the second dummy variable in the model as well? Let's see. The intuition here is that you're basically duplicating a variable. This is because D2 always equals to 1 minus D1. The phenomenon where one or several independent variables in a linear regression predict another is called multicollinearity. As a result of this effect, the model cannot distinguish between the effects of D1 from the effects of D2, and therefore it won't work properly. And this is called the dummy variable trap. If you do the math behind this scenario, you will see that the real problem is that you cannot have these three elements in your model at the same time: the constant and both the dummy variables. I will leave it up to you to figure this one out on your own, and let me know if you have any trouble. I'll definitely help you out. So to sum up, whenever you're building a model, always omit one dummy variable. And this applies irrespective of the number of dummy variables there are in that specific dummy set. If you have 9, then you should only include 8. If you have 100, then you should only include 99 of them. Also note that if you have 2 sets of dummy variables, then you need to apply the same rule to each set. For instance, we could have had a column which specifies the industry in which the companies operate. To build the model in that case, we would have had to perform exactly the same steps and create another set of dummy variables specifically for that column. And then we would include all but one of those dummy variables in our actual model. I hope this explanation was useful and you will never fall victim of the dummy variable trap in your modeling. Next time we're going to cover the different ways you can build a model. We will learn all about backward elimination, forward selection, stepwise regression, and much more. It's going to be an exciting tutorial and I look forward to seeing you then. Welcome back to your Ultimate Data Science course, and I'm super excited about today. I've got an incredible tutorial prepared for you. We're going to cover off a very important topic, and that is how to build models step by step. I couldn't hold myself. I had to add that extra line step by step to the name of the tutorial because that is exactly what we're going to be looking at. I'm going to give you a framework for several different methods, and it's all going to be step by step. So let's jump straight into it. Do you remember the good old days when we had one dependent variable and one independent variable? Everything was easy and we just had a simple linear regression that we had to build and everything worked great. But now, in our data, we have all these columns. Those easy days are gone. Now all of these columns are potential predictors for our dependent variable, and there's just so many of them. And we need to decide which ones we want to keep and which ones we want to throw out. And you'll ask, why do we need to throw out columns? Why do we need to get rid of data? Why can't we just use everything in our model? Well, I can think of two reasons off the top of my head. Number one is garbage in, garbage out. If you throw in a lot of stuff into your model, then your model will not be a good model. It won't be reliable, it won't be doing what it's supposed to be doing. It's going to be a, so to speak, garbage model. And number two, at the end of the day, you're going to have to explain these variables and understand the not just the math behind them, but actually what it means that certain variables predict the behavior of your dependent variable. And you will have to explain that to your executives, to your boss, to people you're presenting to. So if you have 1,000 variables, it's not going to be practical to try and explain that. So you want to keep only the very important ones, the ones that actually predict something. So how do we construct a model? This is the process of building the model, selecting the right variables. So how do we construct a model? Well, there are 5 methods that we're going to discuss of building models. Number 1 is all in. Number 2 is backward elimination. Number 3 is forward selection. Number 4 is bidirectional elimination. And number 5 is score comparison. We're going to talk about each one of them just now. Before we do, I wanted to say that sometimes you'll hear stepwise regression. So stepwise regression actually refers to number 2, 3, and 4. Because those are like really the true step-by-step methods. But sometimes you will hear people say stepwise regression in reference to just number 4. So they will replace bidirectional elimination with stepwise regression, and that's fine. That's normal. That's just because that's the more, as you'll see from what we discussed, bidirectional elimination is kind of the more general approach. And when people say stepwise regression, they kind of by default imply that it's bidirectional elimination, and you have to infer it from there. Okay, so let's move on to our methods. Method number 1, all in. It's not a technical term, I just call it all in. Basically what it means is just throw in all your variables, something we just discussed that we shouldn't do. When would you do that? One is if you have prior knowledge. If you know that these exact variables are your true predictors, you don't have to build anything. You already know that this is the case. You might know it from domain knowledge, or you might know it because you've done this model before, or somebody just gave you these variables and said, please build a model. Well, then you don't really have a choice. You just build the model. The other one is you have to. Perhaps, like, I can't really think of good examples here, but maybe there's some framework in your company that says that you have to use these variables, right? So it's kind of similar to prior knowledge, but it's not your decision. You might want to do it differently, but there is a framework, like maybe a bank, and to predict credit like the likelihood of somebody defaulting on something, they have to use these specific variables. Once again, I'm not sure in which industries that would be the case, but perhaps that could be the case. And number 3, you would use this method if you're preparing for a backward elimination type of construction of regression, which is our next type. So let's move on to backward elimination. Okay, so here comes the step-by-step stuff. You might want to get your pens out and write these things down, because we're going to have a truly step-by-step method now. All right, backward elimination. First thing, step 1, you have to select a significance level to stay in the model. So by default, we're going to go with 5%, so 0.05, and we're going to use it in the next step. So at the beginning, you decide on this significance level. Step 2, you fit the full model with all possible predictors. So you kind of do that all-in approach, which we just talked about, and you put all of your variables into your model. And now we're going to start getting rid of them. Step 3, you consider the predictor with the highest p-value. So remember those p-values that we talked about in, for instance, in Gradle or in any software, you can see them. So after you fitted the model, you'll see the one with the highest p-value. So if p is greater than your significance level, then you go to step 4. And step 4 is you have to remove that predictor. So you remove basically the variable that has the highest p-value. And from step 4, you fit the model without this variable. So there's a star here because I just wanted to remind myself to tell you that if you just remove the variable, obviously you can't just say that, okay, now I've got the new model. You have to actually refit the model. You have to recreate the model, rebuild it with the fewer number of variables. So if you had maybe, I don't know, 100 variables and you removed them, one of them, you have 99 now, well, you have to rebuild it. So the coefficients are going to be different, the constant is going to be different, and you need to perform that step, because once you remove a variable, it affects all the other variables in your whole regression. And so after step 5, you go back to step 3. Once again, you look for the variable with the highest p-value in your new model, you take it out, you remove, so basically step 4, you remove it, you fit the model again with one less variable, and so on. You keep doing that until you come to a point where though even the variable with the highest p-value, that p-value is still less than your significance level. So if that condition p is greater than SL is not correct, then you don't go to step 4 anymore, you go to fin. In this case, fin is the finish. Your model is ready. So as soon as all of the variables that you have left in your model their p-values are less than the significance level, your model is prepared. So that's how the backward elimination method works. Let's move on to the next one. Next method is the forward selection. It sounds like the opposite, and the picture in the top right corner does illustrate the opposite, but it's much more complex than just simply reversing the procedure. You will see that it's a much larger procedure. We start with step 1. Select a significance level to enter the model. And in this case, once again, we're going to select 5%. Then we go to step 2, we fit all possible simple regression models. So we take the dependent variable and we create a regression model with every single independent variable that we have. And then we select, out of all of those models, we select the one which has the lowest p-value for the independent variable. So you can already see that that is in itself a lot of work. Then what we do is we move to step 3. We keep this variable that we've just chosen, and we fit all other possible models with one extra predictor added to the one you already have. So what does that mean? That means we've selected a simple linear regression with one variable. Now we need to construct all possible linear regressions with 2 variables, where one of those 2 variables is the one we've already selected. So basically we add on all of the other variables one by one. So we choose, okay, let's add on this variable, and then let's add on the next one, but separately. So we construct all possible 2 variable linear regressions, and just definitely keeping the variable that we've already selected. So what do we do after that? Out of all of these possible 2 variable regressions, we consider the one where the new variable that we added had the lowest p-value. So if that p-value is less than our significance level, meaning that that variable is a good one, it's a significant variable, then we move back to step 3. What does that mean? It means that now we have a regression with 2 variables, and now we will add a third variable, and we'll try all possible variables that we have left as our third variable. And then out of all of those models with 3 variables, we will go to step 4 and we'll select again the one with the lowest p-value for that third variable that we added. And we'll keep doing that. So basically we'll keep growing the regression model, but not just randomly. We'll be actually selecting out of all of the possible combinations every single time and growing it with 1 variable at a time. And then we will only stop when the variable that we've added, it has a p-value that is greater than our significance level. So when this condition p is less than SL is not true, then we don't go to step 3, we finish the regression. Why? Well, because that variable that we just added is not significant anymore. And we also know that we selected the one with the lowest p-value. So there's no other variable that we can add that its p-value will be greater or will be less than SL. Any regression that we choose from then onwards, the new variable will always be insignificant. And so here we finish the regression, and the trick here is that you keep not the current model but the previous one. And that makes sense because you've just added a variable which is insignificant, so what's the point of that variable? Just move a step back. So that's how forward selection works. I know it's a bit confusing, but just try to wrap your head around it. Maybe read through these instructions one more time. It does make a lot of sense when you kind of picture what exactly is going on. And next we're moving on to the bidirectional elimination. So this one, as you can assume or perhaps guess, it combines the two. Step 1, select a significance level to enter and a significance level to stay. So we're going to select in both cases 5%, but it's up to you what you select. Step 2, perform the next step of the forward selection, meaning that the one that we just discussed, so where new variables, when they enter, in order to enter, they have to be less than the significance level to enter. So basically add on a new variable based on the forward selection method. Step 3, perform all of the steps of the backward elimination process. So now, if you have 2 variables, start getting rid of them and see if you can get rid of any of them. And then move back to step 2. So then grow it by another variable. And every time you grow it by a variable, say let's say you were at 5 variables and you went to 6. As soon as you went to 6, you have to perform all of the steps of backward elimination. So you don't just eliminate one variable if you can. You eliminate 1, 2, 3, however many you can. And then from there you go back to step 2. And so this is a very iterative process. You keep doing that until at some point you cannot add new variables, no variables can enter, or no old variables can exit. And as soon as you get there, then you proceed to the finish because your model is ready. You can't add anything, you can't take anything out. That means you've created the model. So this is one of the more tedious methods. Of course, you would have to get a computer to do this for you because otherwise you'd go insane putting variables in and taking them out. But that's how bidirectional elimination works. Once again, some people call it stepwise regression. And finally, all possible models. So this is the most probably thorough approach, but also the most resource consuming approach, because you select a criterion of goodness of fit. For instance, the Kaiki criterion can be the R squared, lots of different criterions. Then you construct all possible regression models. So if you had n variables, then there'll be a 2 to the power of n minus 1 total combinations of these variables, and that's exactly how many models there can possibly be. And then step 3, you select the one of these models with the best criterion that you're looking at. There you go, your model is ready. So sounds easy, but let's have a look at an example. Even if you have 10 columns in your data, you'll have 1023 models. That's insane. That's an insane amount of models. And we're not talking about columns that you've already filtered out, so columns that that's like in our example, you might have 5 or 6 columns. No, we're talking about when you get a data set that it's pretty much raw, and it has like maybe 100 columns. Like I've worked with datasets with around that, maybe 50 to 100, maybe more columns, and instead of going through them, what this method is suggesting, instead of going through them and picking out the ones that you think should be in your model, you just throw everything in. Well, it's not a good approach, because basically it's growing exponentially. The number of models is growing exponentially, and it's very resource consuming to get a result from this approach. And finally, so where have we come to? We've come to our conclusion. We have 5 methods of building models, all in backward elimination, forward selection, bidirectional elimination, and score comparison. So the one we're going to be looking at in these tutorials, in order to get our head around how to build models step by step and get some practice, is the backward elimination process, because it is the fastest one out of all of them, and you will still get to see exactly how the step-by-step method works, and plus we'll throw in a few extra tricks along the way to make sure our models are very robust. Can't wait to get started. Lots of theory, let's get to the practice. I look forward to seeing you next time.
Hello and welcome to this Python tutorial about multiple linear regression. So in the previous section we implemented simple linear regression in Python, and this time we're going to take a step forward and we're going to add some dimensions in our data set, because this time there's going to be several independent variables. In simple linear regression we had one independent variable, this time we're going to have several independent variables. Okay, so let's implement multiple linear regression on Python right now. So the first thing we need to do is, as usual, set the working directory. So we'll go to File, Explorer here, we'll go to our Machine Learning AZ folder, Part 2 Regression, section Multiple Linear Regression, and here is the folder we want to set as working directory. Let's make sure that we have our dataset CSV file 50 startups in this folder, and if it's the case, we are ready to set this folder as working directory. So to do this, let's not forget to click on this little button here. Here we go, now it's ready. Okay, and now the first step of making our model is to prepare the dataset. And so to do this, as usual, we're going to use our data preprocessing template that we made in part 1. So I'm going to copy all this, copy, and then paste it here. So that saves us a lot of time. And now what we need to do is to change a few things. So let's start with the name of the dataset. That is of course not data.csv, but 50 startups. All right, and then let's have a look at the dataset. But to do this, we need to import the essential libraries, and especially the pandas library, because we are importing this dataset with pandas. So let's execute this. Here we go, imported well. And now let's select this line to have a look at our dataset. So the dataset is well imported. Now let's go to Variable Explorer to have a look at it. Let's double click on dataset, and here we go. Okay, so first of all, the format is not great, so we're going to change it. So as you can see, this is the scientific notation. We will ask for no decimal by replacing 3 by 0, and we will change G into F to have floats. Okay, now it's better. Alright, so what is this dataset about? This dataset contains informations of startups, actually of 50 startups. We have 50 observations. These informations are the R&D spend, the amount of money spent in administration, the marketing spend, the state in which the startup operates, and the profit. And the thing to understand here is that we want to build a model to see if there is some linear dependencies between all these variables, that is the R&D spend, the administration spend, marketing spend, and the state, and this variable, which is the profit. So that means that in the end, we want our model to be able to predict the profit based on these informations here, R&D spend, administration, marketing spend, and state. So that's the thing that needs to be clear in our head. These are the independent variables, and this is the dependent variables. And now that we understand that, we know what indexes to input here for our matrix of features, that is our matrix of independent variables, because simply our matrix of independent variables is going to be all this matrix from here to here, so the profit excluded, containing our 50 observations. Alright, so that's the matrix. And then y here is going to be the last column because it's going to be the dependent variable vector. So it's going to be the vector of profits here. Okay, so now let's change the index. As I told you in the data preprocessing part, we don't need to change the thing here because all my data sets in this course are going to be with the independent variables first and then the dependent variable as the last column. So that's why I put a -1 here to remove this last column to take our matrix of independent variables here. Alright? However, we might need to change this index here, but maybe not. Let's see. This index must be the index of the dependent variable vector, the profit column. So since indexes in Python start at 0, let's count 0, 1, 2, 3, and 4. Unfortunately, we have to change it, but it doesn't matter, right? We just need to replace 3 by 4. Alright, and now it's ready. We are ready to build our matrix of independent variables x and our dependent variable vector y. Okay, so now let's select these two. Command and Control plus Enter to execute. And here we go. X and Y well created. Let's have a look. Okay, so we cannot have a look here because the type is an object. And that's because the matrix contains different types. So it cannot select a single type here. So we're going to look at it from here. X. Alright, so this is our matrix of independent variables. As you can see, we clearly see the 4 independent variable columns with the R&D spend, the administration spend, marketing spend, and the state. And now let's have a look at Y. Well, actually, we're going to have a look from here because since it has a single type, we're going to have a look. Because, by the way, if I double click on this, I have this message. And that's because the type is an object. But here the type is float64. So I can click on this and I can have a look at my dependent variable vector. Okay, and these are all the profits, the real profits. We didn't make any prediction yet. So, okay, right, and we are not ready yet. Now, we need to pause for a second because when you look at this matrix of independent variables, what is striking your attention? Something must be striking your attention, especially if you followed the part 1 data preprocessing. Remember, we might need to do something here. What is it? Well, remember in part 1 data preprocessing, we talked about categorical variables that must be encoded because if they're kept as text, this might cause some issues in the machine learning model's equations. And here, as you can see, we have one categorical variable, which is the state variable, and this variable is not encoded yet. We have the strings here, we have the text, New York, California, Florida, so we might have some issues in the equations. So of course we will need to encode this column here, and so we are going to do exactly the same as what we did in the data preprocessing part. We are going to use the label encoder to encode this column into numbers, but then in order to remove any relational order, we will use the one-hot encoder to create the dummy variables. So let's do this. We're going to go to File Explorer here, and then we will jump back to our previous part, which was the part 1 data preprocessing, which is here. So I'm opening the folder here. I'm opening the section folder. And here is the categorical data Python file, which we will now use to encode our categorical variable state that we have in our dataset. And you're going to see how fast this is. I will just need to open this. Alright. Now I will take this code section here, copy, then I just need to close this, and I'm going to add it here because the encoding must be done before the splitting of the dataset into the training set and the test set. Okay, so now let's encode our variable. So first, we only have one categorical variable, which is the state variable, and therefore it's an independent variable. We don't need to do any encoding of the dependent variable because it's the salary, it's not categorical. So first we will remove this part that was encoding the dependent variables. We don't need it. However, we need this part which is encoding any independent variable. And now we just need to change a few things and we will be ready to encode our independent variable state. So the first thing that we need to change is actually the index of the column we want to encode. So in our template, in part 1 data preprocessing, remember the column was the column indexed by 0, because if you remember correctly, it was the country and it was the first column, so indexed by 0. Here the index of our categorical variable column is the index 0, 1, 2, third index. So here instead of 0 we're going to input 3. Alright, and same for here, 3, good. This part is the part where we use the label encoder to change the text into numbers, and we actually need to do this because we wouldn't be able to use the one-hot encoder directly on the text here because there need to be numbers to create the dummy variables. So here in one-hot encoder we just need to replace the index, and of course it's 3 because this is the index of the column you want to one-hot encode. Okay, and actually now it is ready. As I told you, it's very fast. We just needed to change the indexes. So let's have a final look at our matrix here because this is going to change. So let's just remember how it is. We have the state column in text, and now let's select this. Command and Control plus Enter to execute. And here we go. The encoding was successfully completed. And the cool thing is now, since all our columns are in the same type, the type of the matrix of independent variables, x is now float64. So we can have a look at x from here. So let's have a look. Double click on x, and here it is. I'm going to enlarge this and of course change the format. So as usual, I'm going to put, well, float is already here, but I'm going to choose 0 decimal. Okay, and now we clearly see that we have our 3 columns: R&D spend, administration spend, and marketing spend. And remember, before we had our 4th column, which was the state column here with the text, and this 4th column was replaced with the 3 columns here, which are the dummy variables. And remember, each column corresponds to one state. So, okay, so let's see the dataset. I'm opening the dataset here. So I just want to show you the first observation. So the first observation is the observation indexed by 0. So that's this one. We can check that we have the same R&D spend, 1653.49, 1653.49. Okay, so that's the same observation here. And before we had the state column here, and this observation had the New York state, and the state column was replaced by the 3 dummy variables, each dummy variable corresponding to one state. So since we have 0, 0, and 1 here, that means that this column here is the New York dummy variable column. So that's the New York dummy variable column because the state for this observation is New York, and we have a 1 here, which means that this column is New York. If we take the second observation, we can check that it's the same, 1625.98, 1625.98, okay, perfect. For this second observation, there is a 1 in the first column here, and the state is California. That means that the first column here is California. And finally, the third observation, we have a 1 in the middle here, and the state is Florida, which means that the second column is Florida. So okay, first column California, second column Florida, and third column New York. And therefore, that's how the dummy variables were created. So now I'm going to close this and this. Okay, and now just for the purpose of shaping the intuition, I'm just going to add one line here, well actually one new section. I'm going to call this section Avoiding the Dummy Variable Trap. Okay, and in this section I'm just going to write one line, which is x equals x brackets, colon, comma, and then 1 colon. Okay, so what did I just do? I just removed the first column from x, because by doing that I'm taking all the lines of x, so that's fine. But then by putting this 1 column here, that means that I want to take all the columns of x starting from index 1 to the end. So that means that I don't take the column that has index 0, and therefore I don't take the first column. And why do I do that? Well, the answer is in the title. It's because I want to avoid the dummy variable trap. However, of course, the Python library for linear regression is taking care of the dummy variable trap, so we wouldn't need to do it manually like we do it here. But I just want to add this line to remind you about the dummy variable trap, because for some software or for some libraries, you need to take one dummy variable away manually. So this is just a reminder here, we don't have to do it here, but actually we can do it here. We can select this on and execute. Then we will be sure that our dataset will not contain some redundant dependencies, because that's what the dummy variable trap is about. So we can execute this line. Let's do it. Here it is. And now, as you can see, if I go back to my matrix of independent variables x, it no longer contains the first column, which was California. But for next time, you don't need to do it manually. The library is taking care of that for you. Okay, and now we're ready to make the split. We are ready to split the data set into the training set and the test set. So as usual, we only need to maybe change the test size. So let's have a look. Our data set contains 50 observations. So what would be a good test size here? Well, 50 observations. What about putting 10 observations in a test set and 40 observations in the training set? I think this would make a good split. So actually 10 observations of 50 observation is 20%. So, okay, cool. It's already here, 20%, 0.2. So we don't have to change anything. So that's perfect. We only need to select this, press Command or Control plus Enter to execute. And here we go, perfect. Well executed. Now let's have a look at our X train. Okay, perfect, everything seems good. It contains 40 observations. All right, same for Y train, 40 observations. That's the 40 observations of the dependent variable vector associated to the same 40 observations of X train. And now X test contains 10 observations, and same for Y test, 10 observations. Perfect. And then we are ready, because we don't need to apply feature scaling for multiple linear regression, because the library will take care of that for us. So we don't have to do it manually, and therefore we are ready. Perfect. We are all good right now with the data preprocessing phase, and so we are ready to move on to the next tutorial. Thank you for watching this one, and until then, enjoy machine learning. Hello and welcome to this Python tutorial. Okay, so thanks to the previous tutorial, we are now ready to fit our multiple linear regression model to the training set, because our data is well pre-processed. So let's do it right now. Let's import the library that we need that will complete this job. So this library is the same as for simple linear regression. That is, we're going to import from sklearn, scikit-learn, .linear model, so exactly the same thing as for linear regression, import linear regression. Which makes sense because we're still making a linear regression model, only with several independent variables. Okay, and as for simple linear regression, we are going to introduce our regressor. So regressor here equals, and still the same as simple linear regression, we're going to call the class linear regression parenthesis. Okay, perfect. So by doing that, we created an object of the class linear regression. So the regressor here is our object, and this is the class. So regressor is an object of the linear regression class. And now we are going to fit this object to our training set. And to do this, it's very simple. We will use the fit method by typing regressor dot fit. So that's where we use the fit method. And then we apply this fit method to our training set, that is in Python, X train and Y train. Okay, so what it means is that I first created this regressor object of the linear regression class, and then by applying the fit method onto this object, that means I fit the multiple linear regressor to my training set. So once I execute this line, this particular regressor will be fitted to my training set. And actually we are ready. So let's select this block of code, Command and Control plus Enter to execute, and all good. Okay, so we can see the output here, linear regression, copy x equals true, fit intercept equals true, njobs equals 1, normalize equals false. That's all the parameters of the linear regression class that were taken by default, because we didn't specify them, but that's okay. Here we have everything we need. Okay, so actually that's the end of this tutorial. We just fitted the multiple linear regression to the training set, and now we're going to test the performance of the multiple linear regression model in a separate set, which is going to be the test set. So let's do this in the next tutorial, and until then, enjoy machine learning. Hello and welcome to the final round of multiple linear regression. This is the final round because, as you can see when we go to our data set, we have 4 independent variables and 1 dependent variable. So that means that if we wanted to add a visual step by plotting a graph, we would need 5 dimensions. So that's a little hard to represent. So we won't be plotting a graph for this model, but that's going to be the only one. And so the final round, the final step for this model is going to be the prediction of the test set results. So let's do it right now. It's only going to take us 1 line. It's actually exactly the same as for simple linear regression and any type of regression actually, because you'll see that in the end, all our models' codes will look the same. So indeed, what I only have to write here is to create the vector of predictions that I'm going to call ypred, as for simple linear regression. And then I'm going to use my regressor. And I'm going to use the predict method, here it is, to predict the observations of the test set, which is xtest. Alright, okay, so if I take xtest again, these are the independent variables with the 2 dummy variables here corresponding to the countries. I think it was California and Florida. And then we have the R&D spend, the administration spend, and the marketing spend. So we are going to apply our regressor and especially the predict method to predict what would be the profit of all the startups thanks to the information we have here. And then we will compare some predicted profits with the real profits. So let's click on OK and let's select this line and execute. Here we go, the vector of prediction ypred is ready. So let's have a look, ypred. And here it is, these are all the 10 predicted profits for our 10 observations. And I'm also going to open ytest, which contains the real profit. So we're going to compare the real profit and the predicted profit for some of our 10 observations. Okay, so this column here, this vector is ytest, which contains the real profits, the profits of the 10 startups in the test set, and that's the profits that happen in real life. And this column here is the vector of predictions. That means the profits predicted by our model. So now we're going to compare some of the profits because each of the line here corresponds to the same observation. So for example, if I take this line, this corresponds to the same observation of the startup indexed by 2 in the test set, and here is the real profit and here the predicted profit. Okay, so let's have a look. Let's take the first one. For the first startup here indexed by 0, the real profit is $103,000 and the predicted profit is also $103,000. Here it's 282 and here it's 15. So that's very close. That's an amazing prediction. So congratulations to our model. He made a good job on this one. Now let's take the second one. Second startup indexed by 1 in the test set. And so for this startup, the real profit is $144,259 and the predicted profit is $132,582. Okay, so that's not too bad, but obviously we congratulated our model too soon because it is obviously a less accurate prediction than the first one. Then the third one, the third startup, 146,000 here, 132, okay. Forest, $77,000 for the real profit, $71,000 for the predicted profit, not too bad. Here, not too bad as well. Here, okay. Here, okay, well. Here, perfect, very accurate prediction, $97,000 for the real profit, $98,000 for the predicted profit. That's good. This one is very good too, $3,000 of difference. And finally, the last one, also a very accurate prediction, with only a little less than $2,000 of difference between the real profit and the predicted profit. Okay, so by looking at this test set real and predicted results, we can see that our model did a quite good job, and mostly we can see that there is a multiple linear dependency between the independent variables and the dependent variable. However, in the last section of this part, regression, we will learn some better ways of evaluating our model performance, and we will be using some metrics to measure this model performance. But so far we have this, we can clearly see that there is a strong linear relationship between the two because we were able to fit a linear model to our data set of multiple variables. Okay, so let's click OK. And congratulations, you now know how to make a multiple linear regression model on Python. So in the next tutorials, we're going to do the same thing on R. You're going to see that some things are going to be more simple and some things are going to be better. We will be able to check very efficiently which are the variables that have the highest impact on the dependent variables. You'll see. I look forward to seeing you in the R tutorials, and until then, enjoy machine learning. Welcome to this Python tutorial. In the previous tutorials, we already implemented a multiple linear regression model that we fitted to the training set. But when we take a step back, do you think it's actually the optimal model that we can make with the data set that we have here? You know, because when we built this model, we actually used all the independent variables. But what if among these independent variables, there are some that are highly statistically significant, that is, have great impact on the dependent variable profit, and some that are not statistically significant at all. That means that if we removed these non-statistically significant variables from the model, well, we would still get some amazing predictions. So the goal in this tutorial is to actually find a team, an optimal team of independent variables, so that each independent variable of the team has great impact on the dependent variable profit. That is, each independent variable of the team is a powerful predictor that is highly statistically significant and definitely has an effect on the dependent variable profit. And this effect can be positive, that is, for an increase of 1 unit of the independent variable, the profit will increase, or it can be negative, that is, for an increase of 1 unit of the independent variable, the profit will decrease. And so we're going to divide this final step of building this optimal model using backward elimination into 3 tutorials. In this first tutorial that we are having right now, I'm going to walk you through the backward elimination preparation, because in Python we actually need to prepare something specific, which you will see in this tutorial. Then in the second tutorial we are going to start backward elimination together without completing it up to the end. That means that at the end of the second tutorial you'll get a homework, which will consist of completing what we started with backward elimination. So I'm sure you will have no problem, because I'm going to walk you through the introduction of backward elimination so that you can understand everything and have all the tools to complete the homework. And then in the third tutorial I'll give you the solution of this homework, and we will complete together the backward elimination. So I hope you're excited. Let's start right now the backward elimination. So we will, of course, as usual, need a library, which is going to be the stats models API library. Then we'll just need to do a little trick so that backward elimination runs properly, and then we'll be good to go. So let's do it. Let's first import stats models formula.api. And then let's give maybe a shortcut, because this is a long name, so let's give the SM shortcut for stats model. And now we are almost ready to start backward elimination. We just need to add a column of ones in our matrix of features, our matrix of independent variables. And to understand why, we just need to look back at our multiple linear regression equation, which is here, y equals b0 plus b1x1 plus bnxn. Well, you notice in this equation that there is this constant b0, which is not associated to an independent variable x, like there is no x0 here. But actually there is. We can associate an x0 to this constant b0, it's actually x0 equals 1. So that means that if we set x0 equals 1, then our multiple linear regression equation becomes y equals b0 x0 plus b1x1 plus bnxn. And actually the stats models library that we are about to use right now doesn't take into account this b0 constant. So we will somehow need to add it in our matrix of independent variables, because as you can see, our matrix of features X, which is here, only includes the independent variables like the dummy variables for the state, the R&D spend, admin spend, and marketing spend. There is not this x0 equals 1 anywhere in this matrix of features. And in most library, like the library that we use here to build a linear regression model, it's definitely included the fact that there is a constant b0 in the multiple linear regression equation. But that's actually not the case for this stats models library, which we will use to compute the p-values and evaluate the statistical significance of our independent variables. So that's why we need to do something here, and this something is to actually add this column of ones here in our matrix of features. So we will take our matrix of features X here, and we will just add a column of ones here that will correspond to this x0 equals 1 associated to our constant b0. That way our stats models library will understand that the multiple linear regression equation is actually y equals b0 plus b1x1 plus b2x2 plus bnxn. So let's do this. It's actually really simple. We will just need one line to do this, and let's do it right now. So since we want to add this column of ones here to our matrix of features X, we will start by taking X here. And then we will use this append function of numpy, which will append this column of ones in our matrix of features X. So let's do this. We are going to call np here, dot, and then append, which is our function. Now let's add some parentheses, and let's press Command and Control plus I to inspect the append function. Okay, so what are our parameters? The first parameter is R for array. So of course this is going to be the array to which we want to add this column of ones, and therefore it's going to be our matrix of features X. So here as the first argument, we'll input R equals X. Okay, and then what is the second argument? The second argument is values, and this time, of course, the values are all the ones that we want to add to X. And as you can see, these values are in the shape of an array. That means that here values is going to be an array. And that's perfect for us because we actually want to add a column of ones as the first column of X. So the array that we're going to input here will be a matrix of 50 lines, because as you can see, X has 50 lines, and one column. So we need to add a matrix of 50 lines and one column with only one values inside. And there is actually a trick for that. We can do it very quickly. We just need to use another function of numpy called ones, which will create an array of only one's value inside. So we will need to specify the number of lines of this array and its number of columns. So our second argument is going to be values equals, and then we take our ones function from numpy, so we add here np dot ones, and then since this function ones returns a matrix of only one values inside, we need to specify the number of lines and the number of columns of this matrix of ones that this function ones returns. And if we look at this ones function in more details by inspecting it, pressing Command and Control plus I, well, we see here in the parameters that the first parameter is this shape, that is the shape of the matrix of ones we want to create. And as you can see, we need to input it this way. We need to input some parentheses with inside the number of lines and the number of columns. So here we will just need to input new parentheses in which we add the number of lines, which is 50, and the number of columns, which is 1. But now we need to do one more thing, because otherwise we will get a data type error. And to prevent this data type error from happening, we just need to convert this array of ones here into the integer type. And to do this, it's very simple. We just need to actually add as type and in parentheses int. And now we just need to add the last argument here, which is axis, because you can use the append function here to add either a line of these values or a column of these values to the matrix here, which is our matrix of features X, and therefore we need to specify if we want to add a column or a line. So if we want to add a line, then it's axis equals 0, and if we want to add a column, then it's axis equals 1. So here we'll just add axis equals 1. And now, I'm sorry guys, there's just one tiny little thing to do before this line is ready to be executed. It's related to the fact that right now we are indeed adding this column of 51s here to our matrix of features X, but we're actually adding it at the end of our matrix of features X. And we would like to have it at the beginning. So according to you, what can we do here? We can use a very simple trick to actually add this column of ones here at the beginning of our matrix of features X. What is the trick? Instead of adding this column of 51s here to our matrix X, what if we added instead our matrix X to this column of 51s here? And so to do this, it's actually real simple. We just need to invert and put it in R this way, and then for values we input X. So that right now we are adding our matrix of features X to this one column of 51s here. And therefore, this column of 51s here will appear as the first column of our matrix of features X. And now, of course, I'm going to show you that this actually adds this column of 1s to our matrix of features X at the beginning of the matrix. So let's go to Variable Explorer here. Let's have a look at X right now. So as you can see, X contains all the independent variables without the first column of 1s here. So these are the two dummy variables for state. This is RD spend, this is admin spend, and this is marketing spend. And now, if I select this line and press Command and Control plus Enter to execute, let's now have a look at X, and you will see that now X contains this first column of 1s here. And this column corresponds to this x0 equals 1 associated to this constant b0 in the multiple linear regression equation y equals b0 plus b1x1 plus b2x2 plus bnxn. Okay, so let's press OK. And now, the moment we've all been waiting for. We're going to start backward elimination. But we're just going to take a little break now, and we start doing that in the next tutorial. Until then, enjoy machine learning! Hello and welcome to this Python tutorial. In the previous tutorial, we prepared the backward elimination algorithm by adding this column of 1s here to our matrix of features X, because simply this is required by the stats models library that we will use later to get the statistical information of our independent variables. And now, something to look forward to, we're going to start backward elimination. So let's do this. You'll see it's going to be very easy and fun, and we will get an awesome table that will tell us everything we need to complete backward elimination very easily. So first, let's execute this line, because we didn't do it, we just appended this column of 1s here to our matrix of features X. So let's also execute this line. Here we go. Now the stats models library is imported. And now we're actually starting backward elimination. So the first thing to do is to create a new matrix of features, which will be our optimal matrix of features, and therefore we're going to call it x_opt for optimal. So this is going to be, in the end, the optimal matrix of features, that is, the matrix containing the optimal team of independent variables that are only statistically significant for our dependent variable profit. That is, this optimal matrix xopt here will only contain the independent variables that have high impact on the profit. So we'll see what this matrix becomes at the end, and first what we need to do now is to initialize it. So as you understood, the backward elimination consists of including all the independent variables at first, and then we will remove one by one the independent variables that are not statistically significant. So what we need to do here is actually to take our matrix X of features with all its independent variables. So right now we're taking the matrix of features X, fine, but what we're going to do is that we're going to write specifically all the indexes of the columns in X. And why is that? It's because we're going to remove the index at each step afterwards. So let's do this. I'm first going to take all the lines here with this column, then comma, and then that's where we specify all the indexes of the columns. So we need to specify them in brackets, this way, and then we just need to write the indexes separated by commas. So let's look at the indexes. If I go to X here, we can see that we have 0, 1, 2, 3, 4, and 5 indexes. So let's write all of them. 0, 1, 2, 3, 4, and 5. Alright, so that's xopt initialized as the original matrix of features, that is the matrix containing all the independent variables that we have in our dataset. So now, let's see what we have to do. Let's jump to the slide backward elimination that you saw with Kirill in the intuition tutorial. So the first step is to select a significance level to stay in the model. That means we need to select a significance level so that if the p-value of our independent variable is below this significance level, then the independent variable will stay in the model. However, if the p-value of the independent variable is above the significance level, then it will not stay in the model and we will remove it. Okay, so then this first step is simply to select a significance level, and we will choose SL equals 0.05, that is 5%. Okay, step 1 done. Now let's move on to step 2. So step 2 is actually to fit the full model with all possible predictors. So what we've already done right now is that we created our optimal matrix of features by initializing it to the original matrix of independent variables X. So it contains all the possible predictors, but we didn't fit it yet to our model because remember, we're not taking the regressor that we built in the previous steps, in the previous tutorials. We're taking a new library, so we need to make a new fit of the full model with all the possible independent variables. So let's do that right now. Let's jump back to Python and let's fit our multiple linear regression model to our future optimal matrix of features X opt and Y, because we will need Y to actually make this fit. So let's do this. So things are going to change a little bit right now because we're going to use a new library, which is a stats models library, as opposed to the linear model library. And so we're going to create a new regressor, because the regressor we created here was the regressor from the linear model library, well, actually from the linear regression class from the linear model library. And now we're going to create a new regressor, which will actually be an object of a new class of this stats models library. And this new class is actually called OLS for ordinary least squares. Let's create this new object from this class, and we're going to call it then regressor underscore OLS to, specify that it's the regressor object from the OLS class. So then let's write equals, and then let's call the class. So to call the class, we need to actually call the library first, sm, and then dot, and then that's where we call the OLS class. So OLS, and now parentheses, because as usual we need to specify some arguments. So let's have a look at those arguments. So I'm going to press Command I here, and let's see. Okay, the two parameters, the two arguments that we need to input are ndog and xzog. So it's actually very clear. It specifies that ndog is the dependent variable, so it's going to be y, and xzog is this array with the number of observations and the number of regressors. So typically that is x opt, our matrix of features. But then it also specifies that the intercept is not included by default, and that's why we needed to make all this line here to append this intercept here to our matrix of features. So fortunately it reminds us that we need to add this intercept to our matrix of features when we fit the ordinary least squares model to this matrix. It specifies here the intercept should be added by the user. The user is actually you and me. So that's kind of a relief here, and that's why it's really important to have a look sometimes at the object inspector. Okay, so let's now input the arguments. As we understood, ndog is y, and xzog is xopt. Alright, and now all we need to do left is to fit the ordinary least squares algorithm, which is the multiple linear regression itself, to xopt and y. And to do this, very simply we add here dot fit, which is the fit method, and then parentheses. And that will perfectly do the job to fit ordinary least squares to xopt and y. Alright, so now let's select this and execute. So we just need to select these two lines and press Command and Control plus Enter to execute. And perfect, now xopt is created. Well, it's initialized, and then we will update it until it becomes the real optimal matrix of features. And now, so I think we made step 2. Let's go back to our backward elimination slide. Step 2 was to fit the full model with all possible predictors. Well, this is exactly what we have just done. So perfect, step 2 done. And now let's move on to step 3. So step 3 is to look for the predictor that is the independent variable that has the highest p-value. If this p-value is above the 5% significance level, then we will go to step 4. And if it's below the significance level of 5%, our model is actually ready. So let's do this. Let's look for this predictor with the highest p-value. So to look for this predictor, we will need to use an awesome function of this stats models library, which is the summary function, which will return a great table containing all the statistical metrics that are interesting when building a model. These metrics that can help make our model more robust, like the R-squared, the adjusted R-squared, which we will see at the end of this part in the section evaluating models performance. And of course, we will get all the p-values. So we will get for each independent variable its p-value, and so we will compare it to the significance level to decide if we need to remove it from our model. So let's do this. So as usual, we need to take our regressor object, regressor OLS, alright, and now we need to call this function, summary, and we add some parentheses here because it's a function. we are going to select this line and execute. So press Command and Control plus Enter. And here is the table I've just talked to you about. So as you can see, this contains some very useful information about your multiple linear regression model. So as you can see, we have the R squared here, the adjusted R squared, which we'll be talking about later. You're going to see that we will use these two metrics to make our model even more robust. But now what we're interested in are the p-values. And the p-values are actually in this column, because you know a p-value is a probability. And what's important to understand here is that the lower is the p-value, the more significant your independent variable is going to be with respect to your dependent variable. So these are actually all our independent variables with the constant here, which is the x0 equals 1 variable that we added thanks to this line here. And then we have x1 and x2 that are our two dummy variables for state. Then x3, which is R&D spend, x4, which is admin spend, and x5, which is marketing spend. Okay, so now what do we have to do? We have to look for the highest p-value. We can see that very easily. It's this one with 99%. So we are way above the significance level of 5%. So of course we will need to remove this x2 variable. Because as you can see, if we go back to our backward elimination slide, if the p-value is above the significance level of 5%, then we need to go to step 4, and the step 4 is actually to remove this predictor. So let's actually do that right now. Let's remove the predictor x2, which is our second dummy variable for state. So let's see, let's look at our matrix X, because we just need to keep track of the indexes. So let's see. Constant has index 0, x1 has index 1, and x2 has index 2. So this is the independent variable we want to remove. This is the independent variable that has the highest p-value. So okay, index 2. And so now what we're going to do is we're going to copy this, paste it below, and now we're going to remove our index. So it was index 2, let's remove it. And so by doing this, we actually removed this independent variable, which is the dummy variable for state that had the highest p-value, from xopt. And actually, if we go back to the slide now, we can see that our next step, because actually we completed step 4, our next step is to fit the model without this variable. Well, actually, it's already done here. That's why I prepared this script for you. It's because we just need to copy paste to make step 3, step 4, and step 5 all in once. And speaking of that, this is where I'm going to leave you alone for the homework. But don't worry, you will have the solution in the next tutorial, but really try to implement this yourself, complete backward elimination up to the end, and it will be fun to see if we get the same result. And there is actually kind of a decision to make at the end of backward elimination, so I'm curious to see how you make that decision, make that call, because both solutions are actually great. And we will talk about that in the solution. So good luck for the homework. You're gonna see it's gonna be fine. So basically what you only have to do is to follow this backward elimination slide. And so together in this tutorial we went up to this step 5 here. And now as you can see you have to go back to step 3 and redo the steps 3, 4, 5 exactly like we just did until you find that the highest p-value is not higher than the significant level. And when it's the case, your model will be ready. Okay, so I look forward to seeing you in the next tutorial. I look forward to comparing with you your results to mine, and I'm sure everything will be okay. It will actually be fun and easy to complete this. So thank you for watching this tutorial, and I look forward to seeing you in the next one for the solution. Until then, enjoy machine learning. Hello and welcome to this Python tutorial. Well, I hope the homework went well. I hope you obtained some interesting results. And without waiting, I'm going to complete the backward elimination so that you can see if you obtain the same results as what we are about to obtain, and mostly so that you can see how we complete backward elimination up to the end. So let's do this. So in the previous tutorial we went up to building this regressor without the state independent variable, and that completed the step 5 here of the backward elimination algorithm. And so now we need to go back to step 3 to look again for the independent variable that has the highest p-value, and then we need to compare it to the significant level to decide if we need to remove this independent variable with the highest p-value. So what we simply have to do right now is just to select all this, and all in once this will remove the independent variable from xopt, this will fit the model without the predictor that we just removed, and then we will get the new table with the new results and the new p-values, which is perfect because actually you see in this slide that when we fit this model without the variable that we just removed, we need to go back to step 3, which is of course to look again at the predictor that has the highest p-value, but with the new team of independent variables. So without the independent variable that we just removed. Okay, so let's do this. Okay, so let's select these 3 lines and you will see that it's all going to be very easy now. Alright, so that's the new table. You know, that's the old table and that's the new table, and you can see that in this new table we now have 4 independent variables because we just removed one. So just to keep track of what are x1, x2, x3 and x4, we just need to have a look at xopt. So const is this column here with all the ones, x1 is the first dummy variable for state, x2 is the R&D spend, x3 is the admin spend, and x4 is the marketing spend. Okay? And now, so what is the highest p-value? The highest p-value is actually this one, 94%, still way above the 5% significance level. So now what we have to do is to remove x1, that is the first dummy variable for state, from our independent variables. The dummy variables for state will not be part of the final team. Okay, and now not to make any mistake with the index of x2 here, we need to take our matrix x, make sure to take the original matrix to get the correct indexes, because you know, we're removing the indexes from this x here, so that's the original matrix, so that's this matrix, so we need to be looking at the same thing. So the variable that we need to remove is x1 with a 94% p-value, that's the highest p-value, and x1 is, as we just said, the first dummy variable for state. So that's actually this one, and this one has index 1. So therefore what we need to do now is to remove this index 1 here from xopt. So as usual, we're going to follow our method, we're going to copy that, paste it here, and now we're going to remove the index 1. Okay, perfect. And now are you starting to see how easy it is to implement this backward elimination with this script here? We just need to, you know, do some copy paste, remove the indexes, and then select this block of 3 lines of code here, and just press Command and Control plus Enter to execute. We have our new table here, and in this new table we just need to look at the highest p-value and decide if we need to remove this independent variable that has the highest p-value. So let's see, what is it now? It's actually this one, x2, 0.6, 60%, still way above the significance level of 5%, so that means that x2 here, which is by the way the admin spend, has absolutely no impact on the profit. So we clearly need to remove it. So we're going to remove its index from the xopt matrix, and just to keep track of what the index is and not make any mistake, we need to look at our original matrix x, because same thing, we are removing the index from the original matrix of features x. Okay, and so what is this index? So okay, so we removed the 2 dummy variables, so x1 is therefore the R&D spend, that's the one, and therefore very clearly we understand that x2 is actually admin spend. So that's the variable that has index 4, and that's the index we need to remove. So let's press OK here, and now let's, same thing, copy this, paste it here, and let's remove the index 4. Alright, our model is finally getting ready. Maybe that's the final team, maybe, you know, because that's the constant, so maybe the independent variables with indexes 3 and 5, that is R&D spend and marketing spend, compose the final team of our independent variable that make the best team to predict the profit. So let's see, we'll find out about that right now, and let's press Command and Control plus Enter to execute this. And let's have a look at this new table with therefore only 2 independent variables, so the R&D spend and the marketing spend. And let's look at the highest p-value now. The highest p-value is 0.06. Oh, by the way, there's 0.000 here for this x1. Well, the p-value here is definitely not 0. We cannot have a 0 p-value, but it's just so small, like something with a lot of zeros and then some decimals in the end, but it's a very small p-value, and anyway, it's way below the significance level of 5%, so the R&D spend is definitely a very powerful predictor of the profit and definitely has a high statistical impact on the dependent variable profit. But as far as the second independent variable is concerned, that is the marketing spend, we can see that the p-value is 0.06, that is 6%. Well, it's actually slightly above the 5% significance level that we set. And by the way, we could have set another significance level of 10%, for example, and in that way we would have kept this independent variable. But if we want to follow thoroughly the framework, like the backward elimination algorithm we have on the slide, well, in that case, we need to remove this independent variable. But don't worry, if you still have doubts about that, we will use later some other metrics to make a better decision about that, like to add a criterion that will help us decide with more sense if we really need to remove this independent variable. But this tutorial is about backward elimination itself. We are not talking about improving the model's performance yet, so we're going to follow thoroughly the backward elimination algorithm, and therefore we will remove this independent variable. So now I think it's clear, this independent variable is marketing spend, and of course this has index 5. So let's copy this, let's paste it here, and let's remove the index 5. Okay, and now let's select all this, press Command and Control plus Enter to execute. And here is our final table, with therefore only one independent variable, that is of course the R&D spend, and obviously the p-value is very, very small, which definitely makes the R&D spend a very powerful predictor of the profit. So finally, if we follow thoroughly the backward elimination algorithm, then the conclusion is that the optimal team of independent variables that can predict the profit with the highest statistical significance, the strongest impact, is actually composed of only one independent variable, and that happens to be the R&D spend. And that's it, we are actually done with the backward elimination. So if we take a step back at this tutorial, we can notice that we took quite some time at preparing the backward elimination with this, line where we needed to append this column of ones to our matrix. And then we had to make our regressor using this new stats models library. But then did you notice how fast and easy it was to implement the backward elimination algorithm itself? Because with these 3 lines of code, we just did some copy paste. We had some very efficient look at this table to decide which independent variable we had to remove. And very efficiently, we removed each of the indexes and we obtained very quickly the final result with the final optimal team of independent variables. So congratulations for implementing backward elimination on Python. We're going to do it on R right now. And for those of you who still have doubts about whether we needed to remove the marketing spend, well, don't worry about that. We will use some other powerful metrics that are the R squared and the adjusted R squared, and that, by the way, are here, R squared, adjusted R squared, and will help us decide with more certainty whether we need to keep or not the marketing spend. Alright, so congratulations again. Thank you very much for watching this tutorial, and I look forward to seeing you in the next one. Until then, enjoy machine learning. Hello and welcome to this R tutorial. In the following tutorials, we will be implementing multiple linear regression in R, and right now, as usual, we are going to start with the basics, which is to set our folder as working directory. So right now, I'm on my desktop. I'm going to my machine learning AZ folder, then part 2 regression, and then we want to go to multiple linear regression, and here is the folder. Make sure that you have the 50startups.csv file, and if that's the case, you're ready to click on this More button here to set the folder as working directory. Alright, now let's start with step 1, which is to prepare the data to make our multiple linear regression ready to be built. So as usual, we're going to use our template, the data preprocessing template that we made in part 1, and we're just going to copy this, copy, and paste it here. Alright, and now let's take care of the few things to change. So first we will change the name of the dataset, which is here 50 startups. Alright, 50 startups.csv. We can select this and execute to have a look at our dataset. Here it is, and that's the dataset. I'll remind what this dataset is about. So this contains informations of startups, actually 50 startups, and these informations are some amount of money spent. So for example, there's the amount spent in R&D, administration, marketing, And finally, there is also the state in which the startup operates. And finally, we have a last column here, which is the profit. And that's the profit we want to predict with our multiple linear regression models. And we want to predict that profit based on this independent variables, which are the R&D spend, the administration, marketing spend, and the state. So we are doing this because we are doing a mission for investors who want to know in which startup they should invest their money. And so not only they want to predict the future profits for new startups based on the same information, but also they want to see which independent variable has the highest effect on the profit and which one governs the relationship between the profit and those independent variables. Is there an independent variable that has a highest effect than another one? Does the state in which the startup operates have an impact on the profit? We'll find that out thanks to our multiple linear regression model in R, and thanks to this model, the investors will be able to draw some insights from our results. Okay, so now the next sub-step of the first step data preprocessing is to split the data set into the training set and the test set. But is it the sub-step we need to do right now? I know that the template is suggesting that, but let's not forget that in our data set we have one specific variable which should strike our attention. Well, it's this one, it's the state variable, because it contains categories, which means it's a categorical variable. And remember, when we have a categorical variable like this with categories written in text, this would cause some issues in our machine learning model equations. Because how do you want to make a linear equation with one of the variables written as text? Wouldn't make any sense. So what we're going to do, of course, is to encode the state variable. And to do this, we are going to use what we learned in part 1 data preprocessing. Only we didn't include that in the template because this will actually be one of the only examples where we'll need to encode our categorical data. We put it in a separate file, and so right now we're going to open this separate file. So I'm going to jump back to my folder part 1 data preprocessing, which is here. And here we go. So the categorical data R file is here, so let's open it. Here it is. And right now what I'm going to do is I'm going to take this, copy. So you have the same file, so you can also take it from your folder or take it from the course. And let's go back to our multiple linear regression file and paste that here. Okay, then of course we need to change a few things here. So we need to change the name of our categorical variable. So in part 1 it was country, and here it is state. Okay, same here, we need to change country by state. Let's not forget to align this. This is very important in R and in any programmation language. Here we go. There. And now we need to change the levels. So before, you know, the categorical variable was the countries, and the 3 categories were France, Spain, and Germany. And here our 3 categories are New York, California, and Florida. So let's do it on our dataset. Actually, I will close that because we no longer need it. So here our levels are, we said New York, California, and Florida. Okay, and then the labels, that is the numeric numbers, which are actually factors, the numeric factors that are going to replace these 3 texts here, New York, California, and Florida, are these numbers you choose here for labels. So here we have 1, 2, 3. That means that New York is going to be 1, California is going to be 2, and Florida is going to be 3. You're going to see, I'm going to select this and execute. Alright, and now let's look at our data set. As you can see, the state is now encoded with the 1, 2, 3 values. So 1 for New York, 2 for California, and 3 for Florida. Let's go back. Okay, so the encoding is done, and that's a much better thing for our model. Now, our model has a greater chance to work. And now the last thing we need to do is to split the data set into the training set and the test set. So here, let's not forget to change the name of the dependent variable here, which is not purchased, but profit. Alright, and then we need to change a split ratio if necessary. Let's see, we have 50 observations, so a good split would be to have 40 observations in the training set and 10 observations in the test set. So that makes actually an 80% split ratio, 80% going to the training set. And this is already what we have. Perfect. So we don't have to do anything here for the split ratio. And we are ready to take all of these and execute. And here we go. Let's have a look at our training set and our test set. Here it is, that's the training set. Okay, so it contains 40 entries, 40 observations. Great. We have our encoded variable for state, that's perfect. And then a test set that contains 10 observations and everything looks fine. Alright, so let's go back to multiple linear regression. And the last step is feature scaling, but as for simple linear regression, we won't need to apply feature scaling manually. This will be taken care of with the function that we're going to use to fit multiple linear regression to our training set. So we're all fine, we're all good here. We are ready to move on to the next step, and that's what we're going to do in the next tutorial. Thank you for watching this one, and I look forward to seeing you in the next one. Until then, enjoy machine learning. Hello and welcome to this R tutorial. In the previous tutorial, we took care of all the data preprocessing and we made our data set ready for multiple linear regression. So today in this tutorial, we are ready to fit multiple linear regression to the training set, and that's what we're going to do right now. So as for simple linear regression, the first thing that we're going to do is to introduce the multiple linear regressor, and we're going to call it regressor. So that's the common approach to make a regression model. You'll see that we will create each time a regressor that we will fit to the training set and then apply the predict function on it to make predictions, to make the predictions of new observations like the test set observations. And then as for simple linear regression, we're going to use the lm function, here lm, and in parentheses we're going to input the parameters. Okay, so let's have a look at the lm function here by pressing F1. Here we go, fitting linear models. Let's look at our arguments. So that's the same as for simple linear regression actually. The first argument is formula, but this time you're going to see how we will need to change the formula syntax. For those of you who don't already know the trick, I'll give you the super trick to write the formula very quickly. And then the second compulsory argument to import is the data, and of course it's going to be the training set. So let's first input the formula. So formula here. So remember, in simple linear regression we wrote the formula salary proportional to years experience, and here it's almost going to be the same. But the difference is that we have several independent variables. We have 4 independent variables. In simple linear regression, the dependent variable was proportional to the only independent variable. Well, here it's going to be the same. The profit is going to be proportional to these independent variables. Only the correct way to say it is not proportional, but is the profit is going to be a linear combination of the independent variables. And formula equals profit alt n. And here the idea is to add all the independent variables separated with a plus sign. So let's look at them. It's R, D, spend. I'm using the dot here because in the dataset we have some spaces and R replaced them by dots. So here it's dot, then plus, and then the other variable, which is administration, plus marketing spend, plus state, and that's all. So that's how you express the profit as a linear combination of all these independent variables. That's exactly what means this formula. However, there is a trick to write this formula in a much more efficient way. It's instead of writing all the independent variables here, we can simply write a dot. That's what we can simply write, and that's the exact same equation. R understands that you want to express the profit as a linear combination of all the independent variables. So the dot here just means all the independent variables. Okay, so that's for the first argument, formula equals profit as a linear combination of all the independent variables. And the second argument is data, and as we said, it is of course the training set, because we want to train our multiple linear regression model on the training set and then test the performance on the test set later. Alright, so that's it for building our multiple linear regression regressor. So we're going to select this and execute. Here we go. And now there is something very important to do. And this is something very practical, very useful in R. It's that we are going to look at the informations of our regressor that we just built here. And to do this, it's really simple. We just need to, it's actually like simple linear regression, only here this time it's going to be more interesting because we will have several independent variables and some of them will have a stronger effect on the dependent variable. So we'll see, it's going to be more interesting. And so like in simple linear regression, we're going to write summary of our regressor. Alright, and just press enter. And that's it. I'm just going to move that up. And here we have all the info of our regressor. Okay, so here the first thing is just a reminder of what the formula is. So the profit is expressed as a linear combination of all the independent variables and our regressor is trained on the training set. Okay, perfect. Residuals, we will be talking about that at the end of this part. So let's not focus on that right now. However, that's the important part, the coefficients here. That's what we need to focus on right now. Because as you can see, it gives some info for each of your independent variables. Oh, by the way, state 2 and state 3 here are the dummy variables. And that's because, you know, I told you that the library takes care of everything for you. Not only it created the dummy variables, R knew that it had to create dummy variables for the state variable. And we helped R to understand that because we encoded the state variable as factors. So R did all the job for you because not only he created the dummy variables for the state variable, but also R didn't fall into the dummy variable trap because as you can see, it automatically removed one of the dummy variable to avoid some redundant dependency. So that's perfect. That's the beauty of R libraries as well as Python libraries. In Python, I know we specified a new section to remove the dummy variable, but that was just to remind you about the trap. We don't need to do it. R and Python take care of that for you. So that's great. That's the first thing to notice. And then what I was telling you is that for each of the coefficient we have different information. We have actually the coefficient in the linear regression equation. Then we have the standard error, then the t-value, then the p-value here, and then the significance level. So the most important info by looking at this are the last two columns, the p-value and the significance level. Because these columns tell us about the statistical significance of the independent variable onto the dependent variable. That means it tells us if each of the independent variable has a significant impact on the dependent variable. Okay, so let me first explain what the p-value is. The most important thing to understand is that the lower the p-value is and the most statistically significant your independent variable is going to be. That means that the lower the p-value is, the more impact or effect your independent variable is going to have on the dependent variable. And generally a good threshold to use is the 5% threshold. That means that if your p-value is lower than 5%, then that means that your independent variable would be highly statistically significant, and the more it is above 5%, the less it will be statistically significant. So that's how you must interpret the p-value. And then we have this last column, which is just a faster way of interpreting the coefficients. Because as you can see, we have this line here that explains us about the stars. And basically what the stars mean is that when the p-value is between 0 and 0.1%, then there's going to be 3 stars, which means a highly statistical significance of your independent variable. If the p-value is between 0.1% and 1%, then it's a quite high level of statistical significance. Then if your p-value is between 1% and 5%, then the independent variable is still statistically significant, but will have a less strong effect than the first categories. And then if your p-value is between 5% and 10%, it's borderline. The independent variable might have a certain level of statistical significance, but not that much. Anyway, a lot less than those independent variables that have 3 stars or 2 stars. And then if your p-value is between 10% and 1, then there is absolutely no statistical significance. That means that your independent variable won't have any effect on the dependent variable. So that's very interesting because when we look at our independent variables here, we notice that only one variable has a high statistical significance onto the dependent variable. It's the R&D spend. So it looks like the profit is mainly governed by the R&D spend. That means that it's the R&D spend that has the only strong effect on the profit. So that's a very important information for our investors, because they now know that they shouldn't only be looking at the profit itself by, just looking at the maximum profit to decide where to invest, but also it should be looking at the R&D spend variable. It should be looking at the amount spent in R&D to add another criterion in their investment decisions. So that's a very good info, and basically what all this means is that among all the independent variables here, the only strong predictor of the profit is the R&D spend. The rest is absolutely unuseful. So actually what this means is that we could rewrite this multiple linear regression equation and turn it into a simple linear regression, because since the only independent variable that has an effect on the profit dependent variable is the R&D spend, then the formula could be profit equals R.D.spend, and that would be okay. That would actually give us the same prediction. Okay, so you learned a lot of stuff in this tutorial, but that's very important things to know in linear regression. So congratulations. We only have one tutorial left where we will be predicting the test set results. So I look forward to seeing you there, and until then, enjoy machine learning. Hello and welcome to this R tutorial. In the previous tutorial was a lot of interesting things to learn about R and what it can do to provide insightful information of your model. And now what we only have to do left is to predict the test set results. As for a simple linear regression, it will be very quick. We will just need one line for this, and it's going to be ypred. I'm introducing the vector of predictions here, ypred, and then I'm going to use the predict function. And in the predict function I will just use two arguments. One is the regressor. You have to specify with which regressor you want to predict your test set results, and of course it's with our multiple linear regression regressor that we define here. And the second argument is new data, which is the set of the new observations you want to predict the result. You want to predict the profit. And so of course this new data is going to be the test set. Don't worry if so far we're only making predictions about the test set. You will see that in the next sections we will be making predictions of new observations, which won't be the test set observations but some single observations. You will understand why we will do this, and you'll see that the purpose of doing that is actually going to be pretty fun. So so that's ready. The predict function is ready. It has its two arguments, the regressor and the new data. So we're ready to select this and execute. Alright, and now our ypred vector of predicted results of the test set is ready. So what I'm going to do now is to type ypred in the console to have a look at it. Here it is. So as you can see, this contains 10 predicted results. These are the 10 predicted profits of the 10 observations of the test set. So for example, let's compare the real profit and the predicted profit. So let's look at our test set here. Okay, so let's look at our startups. Let's look at startup number 4. So startup number 4 has a $182,000 profit. And what about the prediction? $173,000 profit. So that's the predicted profit, which is not far from the real profit, so that's pretty good. Okay, what about the second one? $166,000 for the real profit and $172,000 for the predicted profit. Not too bad either. Then third observation, 155, 160, good. 146, 135, not too bad. Then for example, let's look at the startup number 24. Startup number 24 had a real profit of $108,000 and our predicted profit is $110,000. So here we're pretty close. That's an accurate prediction, a good one. Okay, and that's even better for the last two ones, because here it's 99,000, here it's almost 99,000, and 97 here for the last one, and almost 97. So that's pretty good. That's a good model. And remember, that's the model with all the independent variables. But as we saw, there is only truly significant variable, which was the R&D spend. And so if we try to recompute the regressor by only putting the R&D spend independent variable here, you will see that the predictions are going to be the same, with the same accuracy, because the R&D spend is the only strong predictor of the profit. So you can try that yourself. It could be a good practice. You can play around with the different independent variables. So I will let you do it yourself and continue to analyze, interpret, and play around with the multiple linear regression. That's the end of this tutorial. I was very happy to teach you how to make a multiple linear regression model. I look forward to seeing you in the next section, where we'll be talking about a new kind of regressor, because this time you're going to see that it's not a linear regressor. It's going to be a polynomial regressor, and I can't wait to show you how it can give powerful predictions, and we're going to use it on a very funny example. So there will be quite a challenge here, and just to give you a teasing of what we're going to do, we're going to make kind of a lying detector. So I look forward to seeing you in the next section, and until then, enjoy machine learning. Hello and welcome to this R tutorial. In the previous tutorials, we already implemented a multiple linear regression model that we fitted to the training set. But when we take a step back, do you think it's actually the optimal model that we can make with the data set that we have here? You know, because when we built this model, we actually used all the independent variables. But what if among these independent variables, there are some that are highly statistically significant, that is, have great impact or great effect on the dependent variable profit, and some that are not statistically significant at all? That means that if we removed these non-statistically significant variables from the model, well, we would still get some amazing predictions. So the goal in this tutorial is to actually find a team, an optimal team of independent variables, so that each independent variable of the team has great impact on the dependent variable profit. That is, each independent variable of the team is a powerful predictor that is highly statistically significant and definitely has an effect on the dependent variable profit. And this effect can be positive, that is, for an increase of 1 unit of the independent variable, the profit will increase, or it can be negative, that is, for an increase of 1 unit of the independent variable, the profit will decrease. And so we're going to divide this final step of building this optimal model using backward elimination into 2 tutorials. In this first tutorial that we are having right now, I'm going to walk you through the backward elimination algorithm without completing it up to the end. That means that at the end of this tutorial, you'll get a homework, which will consist of completing what we started with backward elimination. So I'm sure you will have no problem, because I'm going to walk you through the introduction of backward elimination so that you can understand everything and have all the tools to complete the homework. And then in the next tutorial, I'll give you the solution of this homework, and we will complete together the backward elimination. So I hope you're excited. Let's start right now the backward elimination. So for those of you who followed the Python tutorial, you will notice that it's actually a little more simple here. Because in the Python tutorial, we had to use another library and another multiple linear regression model to implement backward elimination. And this time, we will simply take the model that we created here, and we will use this amazing function summary of R that returns a great deal of statistical information that can help make our model more robust. And then, same as in Python, we are going to do some copy-paste very simply until we get to the final team of our independent variables. So let's do this. You're going to see it's really quick and easy. We're going to do that very efficiently. And the first step of doing that is to actually take our model, because as I just mentioned, we're going to use the same model to implement backward elimination. So here I just copied the model and I'm going to paste it here. And now we're just going to change 2 things. The first thing is, instead of having this dot here, you know, this dot that represents all the independent variables, we're going to write all the independent variables separated by a plus. Because, you know, the principle of backward elimination is that we will remove each independent variable that is not statistically significant one by one. So we need here to write each of the independent variables so that when we copy-paste this model here, we will just need to remove the non-statistically significant variable from this equation here. Okay, so let's first do this. I'm going to take our data set here to look at the independent variables. So the first independent variable is rd_spen, so let's add it here. So r.d, so you know, as a reminder, there is a dot here because the original name for this independent variable is r space d, and r just replaced the space by a dot here. So it's good to know that if you're working with r and if you have some data sets with spaces in your column names. And then, okay, so what was the name? Dot, another dot, so that means another space, dot, and spend. Alright, so that's the first independent variable. And now let's add the second one. So we need to separate them by a plus. Okay, and what is the second one? The second one is administration. Okay, so here there is no dot, everything is fine, just as it's spelled, right? Administration plus marketing spend plus, and we have one last independent variable, which is the state. So here we don't need to create the dummy variables as we did in Python, because remember, we used here this amazing factor function that encoded this state categorical variable into factors that are 1, 2, 3. And there is no relational order between those categories, so everything is fine. We don't need to create any dummy variables. So that's the beauty of R. And so here, same, we don't need to sum two separate dummy variables. We can take the original independent variable state. Okay, so as I mentioned, there are two things that we would like to change here. The first thing was to replace the dot by all this independent variables separated by a plus. And now the second thing that we would like to do, but it's not compulsory, it's just because I would like to use all the data set to see the correlations, is to replace here training set by simply our data set. So that's not compulsory. We can actually do backward elimination using the training set. But we're just taking the whole data set in order to have complete information about which independent variables are statistically significant and which independent variables are not. Okay, and now actually we're almost ready. We just need to use the summary function, which we actually already used before. And there is nothing more simple than using the summary function. We just need to take the summary function here, and then in parentheses, we input our regressor. Here it is. And now that's actually ready. We're actually ready to start the first steps of our backward elimination. Well, speaking of backward elimination, let's have a look at the slide you saw with Kirill in the intuition tutorial. And here's the slide. So let's have a quick reminder about the 5 steps here. So the first step is to select a significance level that is a threshold for our p-value, such that if the p-value of an independent variable is below this significance level, then this independent variable stays in the model, and if the p-value of the independent variable is higher than the significance level, then it will not stay in the model. We will remove it. So, but the first step is just to select a significance level. We don't have to do anything here with the independent variables. We just need to choose one, and we're going to choose 5%, 0.05. Okay, and now step 2. Step 2 is to fit the full model with all possible predictors. So that's actually what we've just done, by taking all our independent variables in our regressor using the lm function. That actually fits the full model with all the possible predictors, that is, with all the independent variables. Okay, so done. And now what is step 3? Step 3 is to look at the predictor that has the highest p-value. So we will find it thanks to our summary function. And if the p-value is higher than the significance level, that is if it's higher than 5%, then we'll go to step 4. And if that's not the case, our model is actually ready. But don't worry, it will not be that quick. So let's suppose we found the highest p-value higher than the significance level of 5%, then we need to move on to step 4. And the step 4 is actually to remove this independent variable that has the highest p-value. And once we remove the predictor, we're ready to move on to step 5, which is to fit the model without this variable. So that's why, we wrote all the independent variables, one by one separated by a plus, because, once we reach step 5 here, we will just copy paste the regressor and the summary function and remove this independent variable that had the highest p-value from the regressor to build a new regressor without this variable, and that will fit this model without the variable. And once it's done, we go back to step 3 here to repeat the same pathway. That is, once again, we're going to look for the independent variables among the new team of independent variables without the independent variable that we just removed. So we're going to look for the independent variable that has the highest p-value, and same, if the p-value is higher than the significance level, we'll go to step 4, and otherwise our model is ready. So let's do this. We already completed step 1 by choosing a significance level of 5%, and same for step 2, we actually fitted the model with all possible predictors. Well, we need of course to execute the code, and now we will move on to step 3, which will consist of looking for the independent variable that has the highest p-value. So let's do this right now. Okay, so as I just mentioned, we need to execute this to build our regressor with all the independent variables. Well, actually, we don't really need to execute this because we actually executed this code section here that built exactly the same regressor. But just to complete all these steps in this tutorial, let's execute that again. That will not cause any issue. So I'm going to press Command and Control plus Enter to execute. And here we go. Same regressor created again with a different syntax. And that's because we want to remove the non-significant independent variable one by one. Great. So that actually completes step 2. And now let's move on to step 3, which was to look for the independent variable that has the highest p-value. And to do this, we're going to select this summary function with the regressor inside and press Command and Control plus Enter to execute. Let's move that up a little bit. So these informations are very important informations when we want to build a robust model. And that's not only thanks to the informations about the p-values here that will help select the optimal team of independent variables, because below we also have this multiple r-squared and this adjusted r-squared that will help us build even more robust model than the one we're going to make in the next 2 tutorials. Because at the end of this part, there is this section called Evaluating Models Performance to actually improve the model performance. And in this part, we will actually use the multiple r-squared and the adjusted r-squared to finalize our journey towards the most robust model. And you will perfectly understand why at the end of this part. But for now, let's focus on the p-values. So the p-values are actually in this column. And in R, there is actually a shortcut to look at the statistical significance. It's this last column here. Well, this last column doesn't have a name, but you need to look at the stars here. Because as a reminder, the more the p-value is below 5%, our significance level, then the more the independent variable will be statistically significant for the dependent variable profit. And the more the p-value is higher than the significance level 5%, then the less statistically significant the independent variable will be. So in short, the lower is the p-value, the more your independent variable will have high impact on your dependent variable, and the higher is the p-value, the less impact your independent variable is going to have on the dependent variable. And there is this reminder here that says that if the p-value is between 0 and 0.1%, then it's 3 stars, meaning that it's highly statistically significant. Then if the p-value is between 0.1% and 1%, then it's 2 stars, meaning that it's very statistically significant, but less significant than when there is 3 stars. Then if the p-value is between 1% and 5%, then it's simply statistically significant. That is, your independent variables still have some good impact on the dependent variable. And then if the p-value is between 5% and 10%, then it's a dot, meaning that there is definitely a certain level of statistical significance. That is, your independent variable has a certain effect on your dependent variable, but definitely not as much as your other independent variables that are in these categories here, especially for this one. And finally, if your p-value is between 10% and 1, well, there's absolutely no statistical significance. So that means that with what we first observe here, well, we can see that the R&D spend is highly statistically significant, but the rest seems to be not significant. But let's wait for the backward elimination to be completed to find out if our final team is actually only composed of R&D spend. Because by removing some independent variables here, that will remove some possible bias that once some independent variables are removed, we can actually find an independent variable that is more statistically significant than what it appeared to be at the beginning, that is, at the first step here. So let's find out about that, and actually you will find out about that yourself, because this will be the subject of the homework. But don't worry, I'm going to walk you through the first steps of backward elimination and you will complete it yourself. And in the next tutorial, of course, we'll have the solution and we'll complete it together. So I look forward to seeing if we get the same result. Okay, so now let's carry on with backward elimination. So remember, we are at step 3, and the step 3 is actually to look for the independent variable that has the highest p-value, and we can find it very easily. It's actually this one, because indeed its p-value is 0.99, that is 99%, so that's actually a very high p-value, and we are way above the significance level of 5%. So this dummy variable for state 2, is definitely not statistically significant at all. It has absolutely no effect on the dependent variable profit. And by the way, we also observed that state 3 here has a 94% p-value, and there is no way that if we remove state 2, well, this p-value will decrease below the 5% significance level. So we can actually remove this state 3 independent variable as well, because clearly the state has no effect or impact on the dependent variable profit. So we will actually make some kind of a shortcut here, and instead of removing the independent variable that has the highest p-value, that is state 2, we will actually remove both these dummy variables for state, because definitely the state is not statistically significant. So let's do this. Let's remove the state variable from our equation. So I'm going to put that down. Okay, so as I told you, it's very simple. We're just going to copy this and paste it here. And then, so what do we have to do now? We just need to remove the state independent variable from our equation here. And by doing that, we complete step 4. Because if we go back to our slide, step 4 is to actually remove the predictor. Great, and now we can move on to step 5, which is to fit the multiple linear regression model without the independent variable state that we just removed. Okay, so we removed state, so step 4 completed. And now step 5 is to actually fit the model without this independent variable state that we just removed. So let's do this. We just need to select this, press Command and Control plus Enter to execute. And here it is, our new regressor is ready, without the state independent variable. So now we have a team of 3 independent variables. Wait and see which independent variable is going to be kicked out of the team. And speaking of that, this is where I'm going to leave you alone for the homework. But don't worry, you will have the solution in the next tutorial, but really try to implement this yourself, complete backward elimination up to the end, and it will be fun to see if we get the same result. And there is actually kind of a decision to make at the end of backward elimination, so I'm curious to see how you make that decision, make that call, because both solutions are actually great. And we will talk about that in the solution. So good luck for the homework. You're gonna see it's gonna be fine. So basically what you only have to do is to follow this backward elimination slide. And so together in this tutorial we went up to this step 5 here. And now as you can see you have to go back to step 3 and redo the steps 3, 4, 5 exactly like we just did until you find that the highest p-value is not higher than the significant level. And when it's the case, your model will be ready. Okay, so I look forward to seeing you in the next tutorial. I look forward to comparing with you your results to mine, and I'm sure everything will be okay. Backward elimination is very practical on R. It will actually be fun and easy to complete this. So thank you for watching this tutorial, and I look forward to seeing you in the next one for the solution. Until then, enjoy machine learning. Hello and welcome to this R tutorial. Well, I hope the homework went well. I hope you obtained some interesting results, and without waiting, I'm going to complete the backward elimination here on R so that you can see if you obtain the same results as what we are about to obtain, and mostly so that you can see how we complete backward elimination on R up to the end. So let's do this. So in the previous tutorial we went up to building this regressor without the state independent variable, and that completed the step 5 here of the backward elimination algorithm. And so now we need to go back to step 3 to look again for the independent variable that has the highest p-value, and then we need to compare it to the significant level to decide if we need to remove this independent variable with the highest p-value. So let's do this. It's actually already ready. We just need to select this and press Command or Control plus Enter to execute. And here it is. Perfect. So let's move that up. All right. So as you can see here, we have the new formula, profit expressed as a linear combination of all the independent variables except for the state. So that's fine. And here, therefore, we have the p-values for these new team of 3 independent variables. All right, and now what do we see here? Okay, so we can see that, of course, the RD spend is still highly statistically significant with 3 stars here and a very low p-value. And mostly what do we need to do now? We need to look for the highest p-value, and that's actually this one, 0.602, 60%. 60% is definitely a very high p-value, way above the significance level of 5%. So definitely administration is not statistically significant. That is, administration has no effect on the dependent variable profit. So great, that's pretty clear. We need to remove administration from our regression equation. So let's do this. As usual, we're going to copy this, copy, paste, and here we'll simply remove administration. There we go. And now we have our new regressor ready with only 2 independent variables composed of RD spend, which we already know is highly statistically significant, and the marketing spend. Marketing spend, so far the p-value is 10%. Let's see what it will become. So I'm actually going to build this new model by executing this. So Command and Control plus Enter to execute. Here we go. And now let's find out about the statistical results of this new regression model. Let's select this, press Command and Control plus Enter to execute. And here are the new statistical results with only the p-values of the 2 independent variables, RD spend and marketing spend. Okay, so let's see. Wow, there is something interesting here. Can you see it? Well, first, RD spend is still highly statistically significant, no surprise about that, but we actually have one surprise here. Remember, the p-value of the marketing spend was 10% at the previous step. Now it's 6%. And actually we want a dot here. You know, we jumped from this category between 10% and 1 to this category between 5% and 10%. So we actually have a dot now for this marketing spend independent variable. Plus, it's very close to the significance level. It's very close to 5%. You know, for example, if our significance level was 7%, we would have kept this independent variable marketing spend. So it's kind of arbitrary. You know, we don't know if we really need to remove this just because our backward elimination tells us to, due to the fact that we made an arbitrary choice of 5% for the significance level. So, since this is a tutorial about backward elimination, we will actually remove it, but this will not be our final word. Because at the end of this part there will be this section about evaluating models' performance, and we will actually add a criterion to make a better call at deciding if we really need to remove this marketing spend, because right now the call to remove this marketing spend independent variable is arbitrary. So we will remove it because we want to follow thoroughly the backward elimination algorithm, but keep that in mind that it's not our final word about deciding what's the final team is going to be, and we will get back to this problem later in this course, that is later in this part, to make a better call about whether we need to remove yes or no marketing spend. So let's remove it for now. That's actually the final solution, but it's really a good choice of yours if you actually decided to keep marketing spend. You will be proud of this choice at the end of this part. So congratulations anyway if you decided to keep marketing spend. And of course also congratulations to the others who decided to remove marketing spend, because that means you just followed thoroughly the backward elimination algorithm. So congratulations to both of you, and let's finish this backward elimination algorithm, because actually, you know, this is definitely the final step. We have only one independent variable left, R&D spend, and we already know it's highly statistically significant. But let's actually make this model by selecting and executing this. Here we go, model created, and now let's have a final look at the statistical informations of our model. So let's press Command or Control plus Enter to execute. And here are the final informations of the final optimal team. a team that is actually composed of one independent variable, so that's actually funny to call it a team, but anyway, that's just a team of one. That happens, but wait for the final part to see if a team of one can really be the best team. So that's it, we actually completed backward elimination. Our final model is composed of only one independent variable, the R&D spend, and we can clearly see that this independent variable is highly statistically significant, not only because we have 3 stars here, but also because the p-value is really small. So definitely that's a very precious information for the investors that should really look at this independent variable to add another criterion into their investment decisions. So again, congratulations to both of you who either found a final team of only one independent variable, the R&D spend, or a final team of 2 independent variables, the R&D spend and the marketing spend. And for those of you who found another team, make sure to compare the steps that you did yourself with the steps that we did in this tutorial to spot which difference led you to different results. You can always ask me some questions in the Q&A, I'll be happy to help you with your model, but clearly the final team is either the R&D spend or the R&D spend plus the marketing spend. And that's what we also obtain in Python, and that's what you will also obtain in some other programming language or machine learning package. So thank you for watching this tutorial, congratulations again, I hope you enjoyed doing this homework. You will have some other homeworks in the other parts, so you'll definitely practice, which will help you shape your expertise in machine learning. And speaking of machine learning, I look forward to seeing you in the next tutorial, and until then, enjoy machine learning!